Amazing. Modern technology seems to have worked. We are gonna start in 5 minutes or so. Let me know if you can hear my voice okay. Hey, Marco. I discovered the amazing OBS feature that allows me to just project from the whiteboard. Uh, I'm assuming we will not need anything else today, but we'll see. All right, cool. How are people doing? Are you guys excited about the last 10 days of 2020? Hmm. No data. That mean. Oh, okay. Never mind. YouTube is just weird. Yeah, it's kind of crazy. Uh, it's definitely the worst the year for me in my life. But also in some aspects, it's the best year, which is really weird. But overall, it's if I could go back in time and I guess back in time is not the right word. But if you could just cross over everything that happened in 2020 and just delete it, I would be very happy. And I'm sure a lot of people would be. I think I'm in a much better situation than a lot of people. Fortunately for me, but really unfortunately for others. So, but still, it's not all roses. Anyway, enough with the sad things you guys have heard about the 2020 things from a number of other people, and we don't have to belabor this. So, we're gonna start in a couple of minutes. We've done fireside chats a couple of times before. For people who haven't been, the idea is it's just a place to sort of chat about, you know, chat in a somewhat one-sided way, chat about technology, various topics. The way it usually goes is people ask questions in the chat. Have a couple of things I might talk about if there's nothing super interesting. But in general, you guys should ask questions in chat, and I will spend some amount of time trying to answer sort of satellite topics, just talking about the general fields. Pretty much anything goes when it comes to technology. The I might spend more time talking about topics that are interesting to me, right? But in general, super happy to just talk about what you guys want to hear. I think last time we did this, it was a bit crazy. It went for like 3.5 hours. Today I have a hard stop in 3 hours, which is good. So this will not take more than 3 hours, and then if I'm feeling up to it, it'll take 3 hours. If I'm not feeling up to it, maybe it'll take 2 hours in a bit. So we'll see. And with that, let's start. Oh, I should mention. So the um, this beautiful icon was selected before the year 2020, and it's surprisingly topical. Let me actually hold on. Let me switch. Oh, I will not see the chat. Can I pop? Hold on, let me figure out if I can pop the chat out. I can. And then let me figure out if I can overlay this over my. Hold on. All right, so this is great. Oh my god, this setup is so much better than what I was doing last time because now I can see the chat and you guys can see the chat, or rather, like, you can see my chat window open. Anyway, um, let me know also if the mic is clipping or anything like this. It's OBS sort of shows it to be pretty high, but I don't know if it actually clips or if it's fine. I can move the mic a bit further like this. Maybe it'll help. So what I was saying is the picture for the chat was picked, before 2020, and it's very, very topical. But 2020 is almost over, so we are starting now. Okay, awesome. So you guys should ask questions as you see fit. Let me look at the chat. So it was one sort of super open-ended question, which maybe I'll go into a bit before people write more things that they're curious about in the chat. And the question is, why is GPU programming so hard? So super open-ended. Oops. And depending on the background, like I don't know the background of the person who's asking, so I don't know how, to what extent you've experienced the difficulties of GPU programming on yourself, by yourself. But here's maybe the basic idea. So any modern computer, any modern system has the CPU and the GPU. It's actually funny. This is a thing that a lot of people have misconceptions about because people say, whenever we talk about performance in Roblox, for example, people say, well, I don't have a GPU, or it's slow when you don't have a GPU, or something like this. But the reality is, in any modern system, and modern means, anything made in the last maybe 10 years, really, it's really hard, it's really difficult to not have a GPU. So the way it usually works is either the GPU is on the same die as the CPU, which is the case for all mobile systems and also Intel chips, right? So you have Intel integrated, or you have a separate PCI Express card that's, like giant beast that can eat up to like 300 watts of power over there. But anyway, so there's CPU and GPU. And the interesting thing is that both of these today are reasonably general purpose compute units. Like, CPU can do a lot of stuff that GPU can do, GPU can do a lot of stuff that CPU can do. But the programming models are super different. So the way CPU works is there is two instruction sets. Well, there's more than two, but, really, there's an Intel. Oh, hold on. Let me. Okay. There's an Intel and an ARM instruction sets, and there's several versions of them, etc., etc. But for all of these sets, there is exact specs. And what I mean by this is there is a encoding for, like, there's an instruction set and you can look it up online, and there's an add instruction and you know exactly what the add instruction does. And so there is, like, a few hundred of these in a modern CPU, 1,000 in an Intel CPU, fewer than this in ARM, but even in ARM it's like a few hundred. And so there is a spec. The behavior of the instructions is defined pretty much precisely, short of bugs in CPUs that basically never happen these days, outside of, complex topics we won't talk about. And then you have the compilers that, maybe you target C++ as a language, maybe you target C#, maybe I'm trying to avoid talking about interpretation and things like this. Go is a good example. Rust is a good example, right? So these all take your source program and they compile into this binary. And again, for some of these languages, there is a formal spec. The compilers have bugs, so sometimes your code doesn't do exactly what you thought it would do. But you take your source file, like C++ source file, you compile it onto Intel, then you run this binary on any Intel CPU, and it basically has exactly the same results. The distinctions are far and few between. And this is kind of how the stack looks like. Like that's it. There's nothing else really. I'm omitting maybe some, details like if you use Lua or something like this, then really there's an extra layer here. There's some extra complexities around this, but this is kind of how it looks like. And the lower level here, right? So there's only two kind of targets. They are documented. They are specified. There's really, really good hardware validators, meaning there's giant test sets that you never see. Most of them are proprietary. I think all of them are probably proprietary. But basically, when the CPU ships these days, you're pretty sure it works. There's an exception to this. The recent exception, I guess, is Intel TSX, and then there's a few other weird things like this, but like whatever. Basically, the CPU works. When there's a bug in the CPU, which can happen, when there's a bug in the CPU, which can happen, but it happens very, very rarely, you should forget the security stuff that's been publicized a lot in the last few years, because GPUs are just a disaster in that space. When there's a bug that happens, so it's super unlikely that it does, and when it does, manufacturer can actually patch this via firmware update, which is super interesting, but I won't go into details. So anyway, so this whole thing is relatively simple as far as the interface to this goes. Like, there's a lot of complexity in each individual layer, but from the outset, from the user's perspective, this is very simple. The lower level layer is very well documented, very well standardized, like validated, etc. And so you have a program in C++, you write it, you compile it, you run it, it probably works. There is issues around system libraries, etc., that I won't go into. The GPU space, by comparison, is much, much more complicated and much, much more difficult to sort of even explain. So there's many different hardware vendors, right? There is, and so you notice I didn't mention AMD. This is because for the purpose of running the code, AMD and Intel are basically interchangeable. Like, it doesn't really matter as much as you'd think. What CPU you're running on, there's performance characteristics are a bit different, but really, if you look at the instruction tables for modern CPUs, there's so much similarity between them that it doesn't actually matter. So in the GPU land, it's much worse. So in the GPU land, there is, just off the top of my head, I'm sure I will. Hold on, okay. So there's NVIDIA, there's AMD, there is Intel. This is it, thankfully, in the desktop space. In the mobile space, there is still NVIDIA, which also ships a chip there, but also there is ARM, there is Qualcomm, there is PowerVR, and there is a couple others that are, I won't list them because they're not as prominent on the market. But so there is like 6 chips. Within each, 6 companies that do this. Within each company, there's actually many generations of GPUs that are all live on the market with a pretty substantially different architectures. So NVIDIA, whenever you hear like NVIDIA Ampere, NVIDIA Pascal, so all of these are architectures of the GPU. You can some of them are similar to others, some of them aren't. AMD, I think today on the market there's probably 3 different types of AMD GPUs, like the pre-GCN, the GCN, the early GCN, and the late GCN versions, like the RDNA and stuff. Intel goes through many different generations. Intel recently shipped a Generation 10 sort of GPU that is vastly different in some capacity than others. ARM has 2 or 3. Qualcomm I know nothing about because they don't publish anything. PVR has a few. So all of these have a few different kind of actual architectures with actual instruction sets that they publish. I don't talk about minor differences between my understanding is, for example, Ampere versus Turing is kind of, I don't know, there's like a lot of differences. You don't see any of this though, right? So all of this is hidden from you. So then in front of this, there is the graphics driver. Now, unlike the CPU execution, where there is an interface between the program and the GPU, which is the instruction set, so Intel or ARM, and these are rigorously specified and validated. In the driver land, the interface is the API, the graphics API. So the graphics API, if you ship a game, I had a tweet about this some time ago. So you can find yourself in a situation where you target a single architecture plus or minus, which is an AMD architecture. And if you ship your application on Mac, you need Metal and OpenGL. I say and because you can use Metal only unless you want to exclude some people with older Macs from your game. Then on PC, you usually don't use either of these, so you usually use Direct3D of some version, and you're likely to use Direct3D 11 and 12 for complex reasons. On Xbox, you are likely to use Direct3D 11 and 12 for complex reasons, if you ship a cross-gen title like Xbox One and Xbox Series X. You could use only Direct3D 12, but usually games don't find themselves in like this situation. Anyway, so then there is Stadia, which has an AMD GPU, which you have to use Vulkan. And if you will ship your game on Linux, then you might also use OpenGL, but at least that's very similar to the Mac version. And then there's consoles, which I won't name names of the APIs, but there's proprietary APIs. So there's a lot of different APIs. So these are some of the widespread ones outside of the console market. But then also for mobile, there is the ES variants of OpenGL. And there's other versions of, there is like Direct3D 9, which you might use if you have an older game, especially if you support Windows XP, which probably you don't at this point, but 5 years ago you used Direct3D 9 for this. Am I forgetting anything important? I'm omitting again console versions. So there's a lot of different, and OpenGL has like 15 versions, so I'm not going to list them. Here is the thing that's true for all of these. They have varying levels of documentation in terms of the specification. They have varying levels of internal specification. Like some of these APIs are super lax in terms of what's actually required behavior for these APIs. They have very varying levels in terms of testing, but I think for all of these APIs, it's safe to say that compared to the CPU land, there's probably an order of magnitude at least less testing that goes into this, the graphics APIs. And all of these are pretty different in terms of the programming model that they expose to the user. So if you look at Intel versus ARM, you may think, well, there are two different architectures, but actually they're really, really similar from the conceptual understanding. Like there's details that differ, but from a 10,000-foot view, they're very, very close. So what the driver does is it translates the use of this API into sort of instructions, commands, etc. for the GPU. So there's a matrix here in the sense that, for example, you have Direct3D 12 driver, but there are several AMD architectures, and so Direct3D driver has to account for different architectures. Also, there's GPU bugs. GPUs are... So I'm not an expert on chip design, so I don't want to draw conclusions, but there's way more bugs in GPUs that you would expect, hardware bugs that you would see from CPUs. I don't know whether this is due to validation differences or whether the hardware is just more complicated. I wouldn't think the hardware is much more complicated, but I don't know. Anyway, maybe there's. So, it depends on which GPU you look at, but definitely there's mobile GPUs where there's kind of crazy hardware bugs, and there's also crazy driver bugs, and they're not that hard. So I just suspect that there's less resources that these companies are able to spend on validation. Anyway, and so here, point being, here there's many arrows in terms of implementations of all of these APIs, and sometimes these drivers are different, sometimes they are not. The tests are almost always different, the bugs are almost always different, etc., etc., etc. And so then there's the application, right, which has to target all of these. Because these APIs are not easily interchangeable in the sense that the concepts are kind of different between many of these APIs, if you have a single app, doesn't matter what. Let's just say your app is Roblox. This is not the right tilt angle. the app supports multiple of these APIs, but in that support code, it's easy to introduce mistakes because, again, the API concepts are so different. And I haven't even started talking about shader languages, and I won't, because, well, I can just say that. So in the CPU land, you can just say I have one language like C++, and it has really good support for compiling to either of the architectures that I support. There is really mature frameworks around this, etc., etc., etc. In shader land, this is absolutely not the case. It's kind of like really bad compared to the CPU land. And so this is kind of why I think the reason why the GPU programming is so much more complicated than the CPU programming is because the software and hardware landscape is so much more complex, and some of this complexity is inherent to the problem. Like the thing that the GPU does is a bit more complex than the thing that the CPU does, but a lot of this is what people like to call accidental complexity, in that there's like no actual reason why we have all of these different APIs outside of just the platform constraints and the evolution, like the way how all of this evolved. There's no actual reason why the specifications for these APIs are often broken. There's no actual reason why the validation is really bad for some of these. Like, you wouldn't believe how bad some of these things are, okay? Um, so you know, like it's kind of because of the way how computer graphics evolved. This is the landscape that we got. In part, this is because there are so many different architectures with kind of different approaches. But actually, there's a lot of commonality between these architectures, sort of on the lower level. It's just that none of this ever gets exposed. Anyway, so this is why GPU programming is hard, right? So you have to. Oh, and the worst part, right? So the worst part is this: because all of this is underspecified. From the application perspective, it's really not enough to understand the driver layer. You really have to understand the GPU layer as well, even before you get to the performance aspects. Even when you are in the behavior land, like you have to understand the entire sort of end to end, right? Whereas for the CPU land, you can be a C++ programmer who doesn't really look at the assembly, doesn't really understand assembly, can't write assembly, doesn't really know how the CPUs work, and you can write like reasonably efficient programs. You can't write like actually efficient programs, but you can be within like a couple, within 2-3x maybe of what's optimal. With the GPU land, you can't even get your code to work right. In some of these cases, if you don't understand how the hardware works, and you definitely can't get it to be nowhere anywhere nearly fast enough. Anyway, so this is kind of why. Now, in defense of the GPU, like you may think, well, people don't know what they are doing in the graphics land. CPUs haven't this general view of the CPUs from a very high level hasn't really changed since, I don't know, when was C, like it's not even C, Fortran. You can look at Fortran. So it feels like for the last 40 years at least. In the CPU land for the last 40 years, I would say the industry has been perfecting the craft of how do you design a really good CPU, how do you make it work, do you design good compilers, how to make them work, etc., etc. Whereas the GPU land is much more recent in that sense, right? There's parts of this you can look at, like ray tracing, right? Which So PowerVR has an earlier claim to ray tracing, but you can argue the first production implementation is NVIDIA. What is it, 2 years ago? And that's like extra complications in every single layer of the stack, in every single API that supports it, etc., in every single driver, in every single architecture, in every single hardware, software, etc. And it's just really new, right? So all of these things are comparatively new. And so maybe in 20 years, right, we will look back at this and we'll be like, well, actually now GPUs are in a state that's much more comparable to the CPUs, just because there's been a decade of kind of stabilization. But this has not happened yet. Will this be recorded? The answer is yes. The reason why I'm streaming to YouTube, part of the reason is that this thing is just going to be available on YouTube with like no further actions. Like, they usually mean graphics card and not the GPU. So there's no real good like there is a, how do I put this? The differences between integrated and dedicated graphics cards aren't so big that it's meaningful to think about them differently. I would say there's caveats about the memory being shared or not, but other than this, I mean, um, you look at all of these designs. So there's Intel AMD designs, which I don't know if they're going to do more of, but they have this weird chip where I think they got an AMD GPU and then an Intel, not the sort of full sized one, right? Like, so, I think an AMD design, a GPU design, and then an Intel CPU, and they kind of build a system on a chip from this somehow. And then you can look at Apple, for example, right? So Apple M1, it displays really, really, really strong performance characteristics in the GPU space not compared to the top end dedicated graphics cards, but they just don't have enough power there in enough area. Compared to the low to mid end, I would say dedicated graphics cards. And so I just wouldn't differentiate between these two. Like, it doesn't matter as much. Like, if you have half of the area on the die dedicated to the GPU versus you have a separate PCI Express unit, like, there's differences in memory, etc., etc., etc. But again, if you zoom out far enough, it's a graphics processor. It runs very, very special workloads. It has special units. It doesn't matter. Yeah, Snapdragon is Qualcomm. Exynos is a Samsung, I think, CPU chip, so it's a bit different. A lot of the names, so GPUs are different, right? But in CPUs, a lot of the names that you see in the mobile space, they are rebranded. Not just rebranded is not quite fair, but rebranded and slightly customized, I would say, ARM designs. So I think Exynos was different. I'm forgetting the names. There's like too many of them to keep track of. But I think Snapdragon, for example, is not a completely custom. From what I know, not a completely custom CPU design. It's basically an ARM variant. Whereas M1, and so I might write a blog about this at some point. People equate, so with all of this news about Apple, right? People talked a lot about Apple M1 and ARM. And a lot of times people put them in the same sentence, like as if in the same class as if they're equivalent. Like, they say, well, it's really a huge step for ARM. Like, Apple M1 is a huge step for ARM. And it's sort of true, but it's sort of false at the same time, because nobody else on the market can get anywhere close to the performance that Apple can extract from the chip. And just because Apple can doesn't mean others can. So there's a bit of a difference there. But anyway, where was I going with this? Oh, yeah, never mind. I was just commenting and stuff. But yes, right. So Broadcom is another GPU vendor. I should have mentioned this. I guess Broadcom was in Raspberry Pi, so people could actually get their hands on these. We used to support Broadcom on mobile because there's actually phones that use Broadcom. There's not a lot of them, and they're mostly really old, or in case of Raspberry Pi, right, it's a new chip, but it's very it's not competitive performance wise, right? So between ARM, Qualcomm, and PowerVR, all of them have top of the line GPUs in the mobile space that are like reasonably close to each other. So like, you can compare them, they can compete. Broadcom, to my understanding, cannot compete at all. So there's a mesh shader question. I like the 2020 Ti comment. That is true. Hold on, I'm trying to, okay. So with mesh shaders being supported on the new consoles, does it make sense to still support tessellation and vertex shaders in an engine instead of unifying all around mesh shaders? So this is a complicated question. And there is kind of a few ways to answer this, right? I would split this question into two. One, does it make sense to support vertex shaders? Two, does it make sense to support tessellation? So the way I think about this is like if I were answering this question, I would say my answers would be definitely yes and probably no. But let me unpack this. Or if this was a product I would work, I would sort of own tech direction on, I would say definitely not. But let me unpack this. So there's kind of two aspects here, right? One is if you use, for example, if you don't need tessellation, if you don't need geometry amplification, do you still support the vertex shader path? Because these are different. And so I think the answer there has to be yes. Why? Well, so one is you can't really ship your game just on the hardware that supports mesh shaders, right? Today, this means RTX class hardware on PC and RDNA 2 class hardware on AMD side on PC. Which RTX you can actually buy the 20 series, RDNA 2 and RTX 3 series. They're basically non-existent in consumer space as far as I understand because of the supply shortages they had this year. So on PC, right, mesh shaders still represent a small portion of the market. I haven't seen Steam stats in a while. I would ballpark this, if you're shipping a game on Steam, I would ballpark at maybe 5 to 10%, I would say, probably support mesh shaders. And then, 90% doesn't. And then on consoles, you have the current gen, the next gen, which is now the current gen, but you also have the previous gen, right? And, Cyberpunk notwithstanding, I guess, I don't think you can afford not shipping a game on PS4 and Xbox One, right? Now, what this says is that you have to have in your renderer a way to run a traditional rasterization pipeline. There's one other reason which is more subtle, which is why you should be able, your engine should still support this, which is, so mesh shaders are still new and there is recency in terms of the sort of support on the GPUs, etc., right? But there is also performance caveats in the sense that there is actually so I talked about this in my Vulkan streams on mesh shaders. There is presentations from Microsoft about this from the perspective of the AMD hardware. My code is open source, their code isn't, but maybe they'll open source it at some point. It takes time and attention to detail to be able to beat in traditional rasterization workloads without geometry amplification, to be able to beat the old world kind of with the new world, right? And so I would say even from the baseline performance perspective, you should still support the old rasterization path, because then you have an actual benchmark that you can benchmark against. If your mesh shader path doesn't work, you can switch to the old one to make sure to figure out where the problem is. If your mesh shader path is not fast enough, or if you just aren't sure, like, is my code really good, you can switch to the old one and have a baseline. And it's especially important because if you write this code for NVIDIA hardware and then test it on AMD hardware, there may be unexpected kind of performance differences between the two based on the difference in hardware implementation, etc. And so you should have a baseline. But then there is a second question, which is if you want to do advanced things around geometry amplification, etc., should you use tessellation? Should you use like geometry shaders? So I would bias to the no. And again, if I were to make the call sort of for something that I own, I would say definitely no, because I value simplicity in technology, and there is significant problems in terms of the ecosystem complications in both tessellation and geometry shaders. So there's also performance complications, right? So I would like if I were doing this, I would be like, don't want to deal with this, mesh shaders all the way. But this is a very future looking position in the sense that, again, if you're shipping a title today, and for example, if you want to make tessellation has questionable utility in a general sense, but tessellation works really well for terrain rendering. And so you imagine you're making a terrain system, and you really want to use tessellation as a not just as a extra high quality feature on terrain, but kind of as a foundational implementation technique of terrain. Can you afford not doing this at all on older hardware? Probably the answer is no. So this is where kind of it varies, right? If depending on your needs, I would switch the answer between probably no and definitely no. Worth noting that metal today doesn't support tessellation, doesn't support geometry shaders, basically doesn't support tessellation, or rather it does support tessellation, but it does it in a very different way from the way other APIs do, so you have to write kind of to implementation, and does not support mesh shaders. So if you care about max, effectively, right, or if you care about mobile in general, the answer there is unclear. Although on mobile, outside of metal, I would not even bother to use tessellation, and metal doesn't support geometry shaders. So there is that. But so the answer is a bit context specific. I do believe the future is mesh shaders. I wish for a future where we have a graphics API, maybe in 10 years, that removes a lot of the legacy of the graphics kind of APIs and hardware. And one of the things I would definitely cut would be the old geometry pipeline, except for vertex shaders. So I think it's still valuable to have vertex shaders in your API for two reasons. One is it's just a much simpler model to work with. So and I think these things are important. I think people underestimate to what extent they are important. I think Vulkan crazily underestimated this. Oh my god. It's like teaching Vulkan to people is so hard, so difficult compared to teaching metal. But then you look at the actual performance characteristics, and there's like not a quantum leap there, I would say. Which hard to know. But so this is one aspect. And the other aspect is when you're dealing with dynamically generated geometry, vertex shader based. So GPUs have this special unit called primitive assembly, which goes through your index buffer, dispatches all of the vertex shaders in a reasonably optimal fashion based on the vertex cache, etc., etc. And so this unit is actually really hard to replicate yourself efficiently with mesh shaders inside the shaders. So you can beat mesh shaders if you have offline preparation for geometry. Sorry, you can beat the old rasterization performance if you have offline preparation for geometry, and there's really, really significant benefits to be had there if you introduce various forms of cluster-based culling. But it is really hard to beat the old rasterization pipeline. It might be impossible. If you have dynamic geometry, right, with dynamic topology. And so I would say there's probably still a use for the traditional rasterization pipeline from the perspective of both simplicity and performance for some of the use cases. It's just that I would cut tessellation and geometry shaders out of all of this completely. And then it's much, much simpler. We are kind of going back to Direct3D 9 days, right, where there's an index buffer and, a vertex shader. But my understanding is it's not a lot of area to support this. It's not a lot of driver complexity to support this. Even if you're bringing up a new GPU, right? If you don't care about all of the legacy, having support for this is not a big deal. Versus tessellation or geometry shaders, where it's actually rather difficult to implement all of this stuff with hardware and software in a really efficient way. So, communication and synchronization is a whole layer that you don't have to really think about when programming just the CPU. This is true until you get into the multi-threaded programming. But also on the GPU, there's some APIs where you don't have to think about this a whole lot, I would say. So there's OpenGL and like Direct3D 11 and things like this that mostly hide this. Even in Metal, so there's surprisingly little that you have to care about in Metal with respect to these things. There's exceptions around the dynamic resource management, but they usually boil down to explaining to people that, there is a frame in flight, the GPU is a parallel processor, it processes the resources, and then you just have multiple copies and you're done. Vulkan makes these things crazily difficult, right? The D312 was somewhere in the middle, but even for D312, like it's hard to explain. But I guess what I'm saying is, I think we have good software models to sort of work around this. But like I agree with you, this is probably part of the problem. But I feel like if this was, I feel like this should be the biggest problem, and it's nowhere near the biggest problem today. There's tons of issues around other aspects, and I would say that they dominate. Anyway. um, how does part instancing work internally, and would instance meshes be generally faster to render than model prefabs? So this is a Roblox specific question. I will skip this for now because setting this up for people who don't know what Roblox is or how it works is complicated. And also, I don't know exactly what you mean by model prefabs, I guess. Oh, I think you know what. I'm not sure I know what you mean by prefab. So I will skip this for now. Maybe we'll come back to this, maybe we won't. You don't think about uploading your program to the CPU. So again, I agree with this, but at the same time, I don't think this is this is why all of this stuff is hard. Because so if you think about the CPU programming, right? You don't think about using a function that's declared in a different translation unit. But the reason why you don't think about this is because there is compiler infrastructure that can compile this into a single binary, and then at load time patch the pointers. Sometimes you don't have to do this. Sometimes there's different implementations, but there's a dynamic loader and there's a static linker, right? Dynamic linker, I guess, static linker, whatever these things are called on your operating system of choice, that together make sure that when you say foo and pass arguments, this works. In GPU land, you see examples of ecosystems where this is also true. You can look at CUDA. So what you do have to do in CUDA is you do have to separately compile your source, which is an artifact of the sort of build system immaturity, etc., which is not the case. My understanding is in Rust, there are some developments around kind of no hassle GPU programming. You just write some code in Rust in different translation unit with some attribute. You like add 15 crates to your application to make this work, but like then it works, right? So CUDA is a more basic example where you do have to care about the build system setup, etc. And of course, CUDA is not cross-platform, right? But it is an example of you can do these things without having to think about this a whole lot. So what I mean is, again, with enough development around languages and runtimes and ecosystems and enough consolidation and maturity, there's no reason why you can't say, oh, so today you say like set vertex shader, right? And you pass it a binary blob, and you have to compile this binary blob offline from a separate language, etc., 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 etc. There's no reason why in a static language, statically compiled ahead of time compiled language, you can't say set vertex shader and just pass it a function. And what underneath it should do is it should take that function and it should compile it to a different ISA, right? And then depending on the details of the underlying API, which is part of the problem, like figure all of this out. But I guess my point is it's not substantially different from dynamic linking today. The only difference is you have to cross an ISA barrier, right? But it's not like that big of a deal. Again, if you look at ARM or something like this, there's programs that have two ISAs in them, thumb and non-thumb, and it all works. So, like, I agree this is a problem, but I would argue again, it's not really that fun. Like, this is, I don't think it's why. I don't think this is where the real difficulties lie today in terms of programming the GPU. But B, there is complexities around the shader stuff and a whole lot of them. But just the process, like the fact that you have to upload the shader and then kind of bind it, etc., I don't think is a big deal. But also, I think this is a reflection of immaturity of the existing ecosystems around all of this, not a reflection of, it just has to be difficult. So build systems and the time they've spent with them, is it essential accidental complexity? That is an interesting question. Sorry, let me browse this a bit. Yes, so Carlo is making very, very good comments today, which some of them I agree with, some of them I disagree with, but so there's a comment that says 8086 is source compatible with 8008 from 1972. So right, so full disclosure, I was not born at this time, right? So I don't know, but yes, this is what I was saying about, like, it's been 40 years of development where the fundamentals, and if it's from 1972, even more, but I don't think Fortran is from 1972. So there's an important idea of a kind of stable source language interface, I think, also. But the point being, yes, there's a lot of maturity. There's like decades of work on the CPU stack, and it just hasn't been the same for the GPU, right? So you could imagine there's an interesting alternative future where, for example, none of this will ever happen, but like hypothetically, imagine all other GPU vendors disappear. Imagine NVIDIA acquires every single other GPU vendor, which they actually have the money for, I think. I don't think the anti-monopoly committee, whatever it's called, will let it fly. But there is an alternative future where NVIDIA acquires every single GPU vendor out there and then proceeds to build their own graphics API by taking CUDA and extending CUDA to give it rasterization and basically the rasterization interfaces, because most other things CUDA can already do. And then in like 30 years, right, building a complete proprietary de facto solution that everybody has to use. You can imagine an alternative future where if it's not NVIDIA, if AMD did this, AMD is a bad example. There's an alternative future where, for example, NVIDIA changes its mentality from, we build excellent technology that nobody has any business poking around with, to we built excellent technology and we welcome, contribution and collaboration with the world, which is not their mental model today. But in that mental model, and then again, like, NVIDIA acquires everybody, etc., 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 you could imagine this playing out exactly like CPUs played out, where, in a few decades, there is good standards, there is standardized validation, there is really great APIs, and there is documented ISA, because NVIDIA has this thing called PTX, I think, which is kind of like Intel's ISA, in the sense that my understanding is it's pretty stable from generation to generation. There's, of course, extensions around like RTX and whatnot. The GPUs have a different internal binary format, but you could argue that, Intel processors do similar things with microops. So anyway, in theory, I could imagine GPU programming being really close to the CPU programming today, but this requires decades of innovation, and this requires changing of mental models, which will never happen, unfortunately. Like, this requires us to stop this completely crazy business of building a graphics API for every new platform, and then every single game has to deal with this, and then some of these APIs have new shader languages, and that's also completely boneheaded. So like there's many problems around the mental model, like sort of this mental space that these companies are in. But you could imagine an alternative future where this wouldn't have happened, and with the same hardware properties that we have today for the GPUs, I think you would end up with a much better story for writing GPU code. All right, let's. This is the last thing I'll say on this subject, because I think I've talked about this enough. So build systems. So there is a question: build systems and the time developers spend with them. Is it essential or accidental complexity? So the way I view this is it's very similar, I think, to the conversation we had around graphics APIs, where I think most of this. So there are hard problems around build systems in that fundamentally what the build system does is that you have a data transformation pipeline. So you have like sources, for example, for C++, right? So you have source files, and then some of them depend on header files. Some of these header files may be generated by some like a protobuf compiler, for example, right? And then these are compiled to object files using the traditional sort of C++ build model, which is not the only possibility, but it's like a possibility. These object files get linked into, for example, exe files. And then maybe sometimes there is like a precompiled header that you have to generate from CPP and then use it in other CPP files to improve your build performance, etc. Now, there are people who would argue, I think Jonathan Blow would, that all of this is a disaster that should never have happened. But I actually don't really agree with this in the sense that I think it's fine. Like, I think this is actually, to an extent, part of the problem. And so, within that framework, there is an inherent complexity in that you have the build system you have to have a way to specify this graph to the build system. Build system has to understand these dependencies in a very precise manner to be able to build correctly, to be able to build efficiently, etc. And there's a few things that come with this. For example, to specify this graph, this probably means that the build system has to have a language to describe this graph, or you'll end up with a meta build system that has it. This language probably should be Turing complete, because without this, it's really hard to do certain things. And then there's a higher level of this, which is how do packages work with each other. So I would say like there's a part of this problem that is definitely about like intrinsic complexity, right? But I would say that most, like 95% of what people deal with today or more when they work with build systems is accidental. And again, and there is build systems that, to my understanding, do this much better than the status quo. Like I've heard really good things of Bazel. I've heard good things of, for example, so Unreal. The way Unreal builds their code is they have a custom build system called UBT. And like the fact that this custom is unfortunate because this means that your knowledge doesn't translate if you are used to that or if you're used to something else. But I've heard good things about this. So I know of a couple examples like this, right, that do this right. But what people have to deal with today is completely crazy. So let me go on a 5-minute rant because I feel like I can talk about whatever I want, so I will talk about whatever I want. So let me go on a 5-minute rant. Actually, you know what? Maybe I should this will not take 5 minutes. This will take much more. But like whatever. So I will not go on a 5 minute rant. But the way the build systems work today is very very different from. So there is this fundamental problem that you're solving, but then there is how you're solving this problem, and how you're solving this problem is very very complicated, because the golden standard again for native code is okay. So you have CMake. CMake has tons of issues. It's crazy. This is what the rant was going to be about, but then I realized that if I were to give it a fair description and list all of the things I hate about CMake, it would take the entire rest of the stream. But so there's CMake. CMake has a language, right? It is probably Turing complete. I don't actually know. It must be Turing complete. It's arcane. It's like, it's not a good language, but like it has a language. CMake has a lot of different versions, and there's a lot of complications around CMake files that are like compatibilities around CMake files. CMake also has a lot of different like implementation styles. So, for example, when people talk about Python versus Perl, there's two different programming language mottos, and they're a simplification of the problem, but there is one way to do it, and there is more than one way to do this. So more than one. I think there is more than one way to do it. No, I forget. There's like an acronym that Perl people invented back in the day, which is to say that when you're solving a problem with Perl, there's like a billion different ways how you can write your code. When you're solving a problem with Python, there's still different ways how you can do this, but usually there's one obvious and preferred way. And so CMake is in this former Perl-like category where like there's layers and layers and layers of how you could write the same thing 15 different times. And then there's crazy deficiencies. So CMake gained support for precompiled headers in 3.15, I think, which came out last year, I think. So 2019. Precompiled headers are a technology that definitely existed in Microsoft Visual C 6, which is from 1998, I want to say. So 20 years, right? Precompiled headers. Cool story. Which leads to people reinventing the wheel. Anyway, whatever. So there's CMake. But so even CMake alone is really complicated. And most of the complexity of CMake that I'm talking about right now, again, is not inherent. But then there is some complexity in CMake that's inherent, but it's not inherent to the larger problem of you're trying to build a program, but it's inherent to the job that CMake is trying to do. Because CMake is trying to generate build system inputs for other build systems. It's a meta build system. And so then there's like other build systems. But so let's look at, for example, there's Make, or there's Ninja, which are somewhat similar. And then there is Visual Studio and Xcode. And whereas Make and Ninja, they work more from the fundamentals of the build system, like so you have to declare this graph, right? And so the CMake generator has to specify this graph in the language that these tools understand. Visual Studio and Xcode are more difficult because in both of them internally there's like a build graph, but especially for Xcode and also for Visual Studio, like you're not dealing with a pure interface of how the build graph has to be specified. You're dealing with like a project file format, which has very, very different ideas of how the thing has to be structured. And so then these guys have their own build systems. So VS has them as build, and VS Xcode has two now, old and new one. And CMake has to kind of cater to the differences between all of this and has to solve this problem of how do I generate these very, very different outputs from the same input conceptually. And this kind of goes back to the graphics APIs that we've discussed, right? Where there's actually a substantially different mental model that you have to use when you think about the Visual Studio project versus a Ninja file. which is a problem, right? Because it's not just, oh, I'm generating two different representations of a equivalent thing. No, I'm generating very, very different representations of very, very different things. Like the structure is very different. Anyway, and the problems don't even end there, because then these systems, compared to something pure, well built, well engineered like Ninja, these are just bad. Like they're like objectively bad. Like, you know, there's many issues. Like MS Build has tons of problems. I won't belabor this, but Xcode build systems have tons of problems. When Xcode new build systems shipped, in our builds, we weren't using CMake at the time. We were just using like Xcode projects. And so, you switch to the new build system, and then half the time, not half the time, but, like 5% of the time, the build system tells you, well, this file that is required by this other file, both of these are artifacts of the build, and this is just like C++ code. I think it's around precompiled headers again. This file is stale. Please rebuild this file so that the build can continue. And like, oh my god, like, you had one job. Your one job was to take this graph and to build the final product. But you're telling the user, actually, to build this product, you have to rebuild this thing yourself. And so anyway, there's like a lot of problems here. But then there's more problems downstream because, for example, if you're trying to do something, like if you're trying to run some sort of offline process, like if you're trying to generate some of these things, some of these are like artifacts. For example, you might have to interact with shell. And because you might have to interact with like an operating system, like how do I copy this file, right? Because again, the way CMake, you can use CMake language to do some of this work, but you can't use a lot of the CMake language to generate, like to tell the downstream build system what needs to happen when the build is actually going on. So how do I copy a file? Well, now you have to either use shell or use some of the CMake commands that actually support this as a first class. And the shell is different on different platforms. And so it goes on and on and on and on, right? Like this is not very different from the graphics discussion that we just had, where just like through how this evolution process worked, we ended up with something really, really arcane with tons of different things around, tons of different like software technologies around this problem that aren't they aren't focused, like they usually aren't solving one thing and doing this well. So yeah, there was a comment that Ninja actually does do this, and yes, this is true. Ninja is pretty cool. All of them are complicated, and this is like half of the story. So I haven't even started talking about the dependencies between libraries, which I just won't go into. It's like really hard. And so based on my prior experience of, I actually worked on build systems, and I worked with build systems a fair bit. Like I'm not like an expert in the state of the art, but I've worked a lot with sconce. I've worked on patches to sconce and custom things around sconce. I worked a bit with WAF. I worked with Jam, a bit with KJam. I worked a lot with Jam Plus. I'm not an expert in Make, but I can write really good Make files. I'm really not an expert with CMake, but I have to suffer the CMake problems. I wrote a bunch of extra stuff around MS Build, and I also wrote a custom. Oh, sorry, I'm not scrolling this here. The list goes on and on and on. And I wrote a few custom build systems. I wrote one custom build system in F# for asset builds. Actually, maybe two. And I've read a bunch of papers around this, which is to say, basically, I'm not like completely ignorant of the state of the art. I'm reasonably familiar with all of this stuff, and all of this stuff does not inspire. How do people? Right, it doesn't spark joy. Does not spark joy. But again, I think a lot of this isn't intrinsic to the problem, because I think the problem is this, right? The problem is, here's a graph of stuff to do. How do you describe this graph? So Ninja doesn't solve the problem of how to describe this graph, for example, very well, right? Because With Ninja, it's basically an assumption that you have to have a meta generator, like a thing that generates your build graph. And Ninja doesn't really have a strong notion of packages and or a notion at all of packages and dependencies, right? But so there's what is called Cargo, which is a build system for Rust. My understanding, so I'm not very familiar with Cargo. When I used Rust last time, it was before 1.0, and Cargo was very immature back then. Mm. My understanding is people are very happy with Cargo in general as both a package management system and a build system. And so maybe Cargo is an example of how you solve this problem without, you know, a lot of the accidental complexity. But I think the build systems that people deal with mostly are just full of like accidental complexity, and there's a small bit of intrinsic complexity that they don't get right. Oh yes, I have tried. I have used Premake. I have used Premake 4. I've tried Jenny a bit, which is a fork of Premake 4. I don't remember. I have not looked at Premake 5 at all. I don't know if it's finished. Premake, again, as an example of a meta build system, is not a build system, right? So it doesn't really solve or it solves a problem, but it doesn't solve the problem, because the problem is, how do I build the final product that is going to ship to my users, right? Or how do I run tests or things like this. And CMake in general is crazy. Like, it's really sad. CMake is like sort of, I hesitate to call CMake C++. Maybe CMake is very close to OpenGL, because yeah, actually CMake might be similar to OpenGL in many ways. Like, it's pretty bad. It was a de facto standard at some point for large areas. It probably still is, of computer graphics. It has tons of versions with crazy compatibility issues between them. It doesn't have formal specific. Maybe CMake is worse. Anyway, let's not talk about CMake. I'm just going to be unhappy if I talk about CMake more. But yes, so I think there is a problem in build systems that has to do with essential complexity, and it's actually a rather interesting problem, because you can think about the how you structure these dependencies, how you discover these dependencies is an interesting problem. For example, and there's different models there. For example, the F-sharp build system that I've built for asset builds, it was cool in that it kind of relied on coroutines and coroutine dependencies to be able to discover, to be able to dynamically transform the build graph as you build it. Because the problems you often run into in these things are things like this. Here's like a very basic example from a asset build world. So you want to build a scene, like a 3D scene. So you want to build a, let's use the GLTF terminology just in case people are familiar with this, but basically you want to build a file that has your geometry in it, and then you want to build a bunch of texture files. So you would use like DDS and proprietary formats, etc. How do you build this? What do you build this from? Where you have to build this from some source art. So let's say PNG, and there's much more complicated possibilities where the mapping between textures is not one-to-one, where you have multiple source layers that you combine in like interesting ways, but like let's not go there. And then you have something that you produce your final kind of delivery binary from. What is this something? Well, um, let's say you use FBX as an interchange format, just for the sake of the argument. But then with FBX, you might want your artists to export FBX files and to store that in your version control system. That has some upsides, that has some downsides, because the export settings control kind of what and how it ends into the scene. So you might want to automate this process, so maybe you have the actual source files. MA is Maya's ASCII, so maybe you use MB for Maya binary. But then the difficulty is that the set of textures that's used for your Maya scene is actually a product of looking at the Maya file. And so really the pipeline is usually, or the pipeline can be one where you discover this set of files, and so this entire portion of the build graph, by reading, for example, the FBX product of the Maya to FBX export, because it's hard to read the Maya binary files. It's actually not hard to read the Maya binary files. I actually had code to do this, but whatever. But so this means that you might have a build pipeline where you take your Maya file, you automatically, your build system builds an FBX file from this, and then it has to parse that file, discover the dependencies, these texture dependencies, form this new part of the build graph, but then also connect the dots here, because context where you want to use the GLB file, for example, you may want to package this into like a pack file or zip file or something like this, right? You want to know about all of the dependencies of that file, which are these like KTX files, but then all of these nodes are dynamically discoverable, right? So these are like interesting problems in the sense that there's different ways how you can model the process of building this graph, the process of like executing this graph, and also the process of constructing this graph. So there is an interesting problem there to solve, but 90% of what you actually deal with is stupid stuff. Does Vulkan give the programmer the most control of the GPU hardware out of all the APIs? No. So if you include consoles, the answer is emphatically no. The APIs that you get on PlayStation consoles, basically all of them, doesn't really matter like which number, are much lower level than Vulkan. In fact, so then you can look at Metal, right, and D312 as points of comparison. So in case of D312, I would say the answer is it's very close, but then if you include the hardware vendor extensions, then Vulkan gives you a bit more control in some places. If you compare it versus Metal, the answer is difficult to describe. So Vulkan, the thing to understand about Vulkan, so there's this interesting notion when these APIs were brought up, and I don't know that I'm using this terminology correctly all the time. So, you may see me accidentally say, Vulkan is a low-level API. And that statement is actually false. Vulkan is not a low-level API. A low-level API is an API that allows you to control the hardware in using an abstraction, because there is always an abstraction that's like pretty close to how the hardware works. This is super not what Vulkan does. The more correct term that people use is explicit API, which is to say that Vulkan gives you a way to tell the driver more explicitly what problem you're solving, what kind of properties of the solution would you like the solution to have. But it doesn't really map to the underlying hardware like one-to-one, not even close. And part of this is it's mostly necessity, right? Because so we had this 6 or 7 or whatever vendors, and I was saying that some of these vendors have different implementations. Different like architectures, right? So for example, Intel is a great example because Intel actually documents this in their public documentation, I think. Yes. I don't think I've read any Intel proprietary documentation, so I think it's all public. So Intel is an interesting example because they're the latest revision of the Intel architecture, which you can actually buy, like whatever you buy from Generation 10 Intels. So it's a tiled architecture now, or it supports tiling. So older Intel chips used an immediate mode rasterization pipeline where you have your vertex shader, you run your vertex shader on the triangle, on the vertices of the triangle, then there's the primitive assembly unit, etc., etc., etc. The new units support optionally, I think, a mode. I think they call it posh. Not posh, sorry, but like there's a tiler, and tiler has a concept of posh, which is a position shader, I think, where you take your vertex shader, and this is not an Intel. Like Intel didn't invent this. This is how some other mobile GPUs work as well. So you have your vertex shader, which computes like position, like texture coordinates, like normal, and other attributes. And so the driver generates a second shader from this, which only outputs position. And then it runs this on your geometry. Then it takes the resulting triangles, it classifies them into tiles. And then for each tile, it takes the actual vertex shader, runs this for the triangles that are inside the tile, etc., etc., etc. Nowhere in Vulkan there's a concept of position on the shader. Like, it does not exist. And this is just like one example off the top of my head. There's thousands of these examples. If you're curious about the topic, I think I covered this a bit, not to the extent that it deserves being covered, but I covered this a bit in my Vulkan performance article, like optimizing Vulkan render, something like this, which you can find on my blog, which, if you need a URL, it's zoops.io. But really, I don't talk about this enough there because really the topic is super deep. So, so yeah, the answer is kind of like not really, but also this is not really the way you should think about Vulkan. Vulkan doesn't really give you control over the GPU hardware. It gives you a way to ask the driver to do something. So, for example, here's an example of a different API that I can talk about publicly, right? And of an aspect of this API that does give you more control of the API, even though you would classically not think that. So let's say you have a tiler. So, like, I talked about this briefly in Intel context, but you have a screen. So the hardware splits the screen into tiles. And so then it takes your geometry, then it classifies triangles into tiles, and then it says, I want to draw this tile, draws all of the geometry here, runs the vertex shaders, runs the pixel shaders, and then copies the result of this back to the main memory. Cool. Let's say you want to run two passes. What's the simplest example? Here's the simplest example. Let's say you render your geometry into a texture, and then you run one more step, which is a full screen quad or full screen triangle or whatever, which takes the output of the previous stage, which, let's say, was in HDR format, so like floating point targets or whatnot, however you want to encode this, and this step does tone map and color correction. And so HDR content goes in, LDR content goes out. Cool. So the way you model this in graphics APIs, in traditional graphics APIs, is you render this thing to texture, and then you have a second render target, and then you have a shader that reads from the first texture, outputs the pixel. In tilers, what this means is that you have to render each tile, store each tile to main memory, and then read each tile again from main memory, and then do all of this conversion, etc., and then write it out. So you have to do one HDR write from the rasterization pass. Oops, sorry. One HDR read. So this is when you have the geometry pass, geometry rasterization pass, and this is when you have the post processing pass, and one LDR write. Now this is two more HDR accesses to main memory than you actually, strictly speaking, need on a tiled architecture. You may say, well, can't you do the tone map and color correction in the fragment shader of the geometry pass? And the answer is maybe, but then once you start working with transparency, the answer is actually no. And so in the general case, the answer is no, right? In the general case, you have to go through this pipeline. So what you can do on tiled architectures, though, is that if your tiler supports it, so you have this tile that you have processed that's like comes out of this big texture. So you wrote HDR content to it. But instead of writing this tile to main memory, what you can do is you can write then and there, say, well, let me just process this with my shader that does tone map and color correction, right? Because in this tile, you already have done all of the blending work, etc. in HDR space. So you can do the HDR to LDR conversion in the tile memory, which is way faster. It has like crazy bandwidth compared to the main memory. And then you can do the LDR write. This is the optimal way how to do this on tilers. You probably are using compressed HDR formats, which means that probably this is 4 bytes per pixel, 4 bytes per pixel, 4 bytes per pixel. So, this cuts your bandwidth in 3. If for whatever reason you can't use the compressed formats and you have to use the full like half precision floats, this cuts your bandwidth in, what is it, 5? Yeah. So this is like a big deal. The way you do this in Vulkan and Metal is very different. So in Vulkan, the way you do this is using this render pass subpass relationship. So you have two subpasses. One does geometry and one does color correction. The geometry pass outputs data to a texture, which is called attachment in Vulkan. And you use this attachment as the input attachment to the color correction pass. And then in color correction pass, you have a shader that instead of doing the traditional texture lookup, it just does an attachment read. And these guys are restricted to just the current pixel that you are processing. So you can't read from some pixel elsewhere. You have to read the current one. And then you do the computation. And then, so if you run this on the tiled architecture, what happens is with a good driver, like what I described earlier, right, where you have tiles and in tile memory, this operation is performed and then the result is written. If you run this on a traditional immediate mode renderer, instead what happens is the sort of normal thing where you write the whole thing to memory and then you read the whole thing from memory. So you don't get to save the bandwidth this way, but like this is fine. What happens in Metal instead is that if the device that you are targeting supports this feature, which is called there's a thing called image blocks, and there's a thing called, I think, tile shader. And so what happens on Metal instead is that you say, I want a tile shader that performs this color correction. And instead of using the textures to communicate this, I'm going to use these image blocks. So I'm going to use an image block that's the size of the tile. And in my tile shader, I'm going to take this image block, sort of read data from it, and then compute the result and then write it out. And this code will only work if you actually use, I think this code will only work if you actually use hardware that supports tile shaders. But the difference here, right, is that in Metal's case, we said, okay, hardware supports the concept of tiles. Hardware supports some memory that is per tile. This is limited memory. And we are going to code for this hardware. This is what I would call a low-level API. Again, people usually don't associate Metal necessarily with low-level, but in this specific case, it's actually a low-level API, right? It actually allows you to use the hardware, to code for the hardware in an abstraction that is really close to what actually happens there. And this gives you more flexibility. You don't have to read from just the current pixel. You can read anywhere from the image block. You have to respect the tile boundaries, right? So it's hard to do like blur in this case. But in Vulkan's case, it's like impossible to do blur or any kind of processing effect where you need some other pixels. What happens in Vulkan is that you have an abstract description of your solution, and then a driver that maps this abstract description to the hardware, in ways that you don't understand. Maybe the hardware does support tiling, but for whatever reason, the driver decides it can't use this. This actually does happen in practice in some cases. So you think you're using the hardware optimally, but you aren't. And this is because the API is not actually low level. It doesn't actually allow you to specify the solution to the problem. It allows you to sort of declaratively talk about the solution or like the problem. It allows you to specify the problem statement, right? And then the solution is actually manufactured by the driver from this. So hopefully this is reasonably clear. This is why I don't think of Vulkan as a low level API at all. It's certainly verbose. It's certainly explicit. It's not really low level. And so it doesn't give you as much control of the hardware as, some other APIs do. Any thoughts on RISC-V? Missing a killer product, something like Raspberry Pi. Yeah, so I know people are crazily excited about RISC-V. I think RISC-V is really great from the perspective of... So, I talked about all of these problems with graphics around mental model that the companies have. And so one problem with the CPU instruction architectures today is that, for example, there's Intel's architecture. Can you build a CPU today that uses Intel's architecture, uses Intel ISA, so instruction set architecture, right? Can you build a chip? The answer is really complicated. There's like patents involved. There's probably licensing fees. Like, I don't know how this works, but the answer is complicated. There is ARM. Can you build a chip today that targets ARM instruction set without actually using an ARM design? The answer is yes, but you have to pay money to ARM. I think it's called an architectural license. I don't know what the numbers involved are. I would ballpark this as like a few $1 million a year. I don't know what they are. I don't know if you have to pay licensing fees to ARM. I'm hoping not, but who knows? So, for example, as an enthusiast, can you build an FPGA-based like ARM thing? I don't know if you can build it, but you definitely can ship it. It would violate ARM's ISA agreement. And so you can do this with RISC-V. And also, I think RISC-V gives you designs for some example CPUs for free also. So in the micro-embedded space, my understanding is that RISC-V is a big deal because, it allows you free access to a lot of the stuff that was proprietary before. If you look at this purely from the ISA perspective, I mean, it's not interesting at all to me. So you look at x64, you look at ARM, they're very different in some ways, but also they're very similar in others. You look at RISC-V. Is RISC-V a good instruction set? I mean, I looked at this a bit. I'm not an expert on RISC-V. It seems fine. Like, I'm sure people who are experts on this stuff would find things to complain about. I'm not really an expert, but also I haven't really read this in detail, so, it's probably fine. It has this weird embedded idiosyncrasies around, I don't know, I think integer division probably isn't part of the ISA, and then you probably have some extra, extension that you can use to get it. So if you have a RISC-V CPU, can you actually divide integers on it? I think the answer in general is no, unless it supports, some extra extension. So, there's, weird things like this. There are vector instructions that I've looked at. It's okay. I'm not a huge fan. It's probably fine. It misses some things that I would consider important, but it's not bad. It's okay. So, is it a good development? Yes. I think it's a good development primarily from the perspective of, okay, if the world adopts RISC-V to some extent, there's going to be easier access to custom hardware, which might be good. And in general, this would clean up a lot of questions around ISIS in terms of the licensing fees. If you just take this at face, from the ISA perspective, removing the licensing portions, is it good? It's fine. There's nothing to write home about there. So that's kind of my take on RISC-V, right? It's is RISC-V interesting? Yes. Am I interested in RISC-V? No. There is no value that I see in RISC-V. There is misinformation around this as well, because there is this there was this recent development that some company built a RISC-V processor that is supposed to be super efficient, like beats everything else under the sun. And people say, it's a property of RISC-V that allows people to do this, and I don't think that's true at all. I think it's just a different design space and doesn't say anything about the applicability of RISC-V in, for example, smartphones or desktop computers. And so, again, like, um, I'm not intellectually curious about RISC-V because, um, from my point of view, once you've looked at two ISAs, this is just a third one that's not substantially better in any meaningful way. And because of this, right, I'm not like super excited about this. Um, and it's kind of one more thing in the sense that imagine there is the RISC-V processor. Okay, now there's some code that you have to write again for the RISC-V, and now there's like a baggage of issues with that. For example, if it was possible for ARM to open source their instruction set, I would be much happier with that development versus a RISC-V development. But obviously ARM is like a company that has money to earn. It's worth 40 billion apparently. So anyway, so but I understand that people in the embedded space are much more excited about this again because of the accessibility that it provides. Somebody has a 6,000 series GPU. Hmm. Is that even legal these days? All right, I'm really like the chat is backed up. Let me look at this stuff. Yeah, so like if people ask Roblox specific questions, I will only cover them if we have time. I don't think we'll necessarily have time. So if there is parts of the Roblox question that I can cover that are generally applicable, I will still answer this. But if there is a question that requires, like, for people who aren't familiar, 15-minute explanation, and then the answer is not really useful outside of the context, then I probably won't talk about this. CUDA is used with measurements. Yeah, so CUDA is used like everywhere. So NVIDIA basically dominates the machine learning market today. And so if you look at any machine learning framework, it has really great support for CUDA, or if it doesn't, it's not useful. And then it has pretty bad support for anything else. I think CUDA, so I looked at this at some point, I forgot the answer. I feel like there's a licensing restriction on CUDA in that you can't re-implement CUDA. So I think AMD cannot legally implement their own version of CUDA that is like binary compatible, etc., with CUDA itself, which is a way to vendor lock, right? So, good job NVIDIA as usual. But as a technical product, CUDA is most excellent from what I know about this. I've played a bit with CUDA. I haven't played with CUDA in the last 5 years. I think it's made some developments in some deep GPU computational topics I won't go into right now, but it's pretty good. And it works really well from what I know. It's pretty ubiquitous, etc., etc., etc. Compared to this, you can look at efforts like OpenCL, and it's just like a disaster. OpenCL basically doesn't really work as far as I'm concerned. AMD has some custom thing called ROSM or something like this, ROCM, which, my understanding is it's also kind of not good. So, but yeah, CUDA is pretty great. We need centralized GPU technology now. Yeah, so this is like an interesting thing, right? Where at some level you want centralization, but then on some other level, if you achieve the centralization by one company taking control over the market and then not letting anybody else in, then you get really, really, really terrible effects on the whole system. The whole Intel story is kind of fascinating because this is kind of how Intel worked, right? And like Intel took the market over, but then AMD entered the market, and then AMD had really, really strong CPUs, and then they had a period, like a decade of really, really not strong CPUs. But now, there's just no reason to buy an Intel CPU anymore. Primarily because Intel just hasn't been doing a very good job. But it's kind of interesting that if the software and hardware market were in different place like 40 years ago, maybe things would have, like, in fact, my understanding is 50 years ago, things were much closer to what today's GPU landscape looks like. I mean worse, right? In the CPU land, where there's all of these different architectures, and you can sort of use C wasn't even there at the time. You can sort of use Fortran, but really probably you just use assembly and then you rebuild you rewrite your code for the target architecture. So like things were pretty bad in this space, but it is interesting that Intel took the market over, but it didn't result in Intel monopolizing the market, or it did for a while, but it wasn't a situation that the industry couldn't get out of, right? And so if we could get to the same space in the GPU land, that would be great. I don't really want to get to the space in the GPU land where really like Nvidia is actually the only GPU vendor, and actually like all of the hardware that is manufactured as GPU and all of the software and all of the APIs is all Nvidia controlled. So I don't think it would get there. Anyway, it's just that right now I don't see how the current situation will improve as well. So have you tried playing with tier improvers? I have not. Mm, I played with Idris long time ago, but it was super hard to get it. So yeah, like no, I am not very knowledgeable about this field. I know little things. I know little things about the applicability of this in the sense that, for example, my understanding is there is a sort of proven C compiler now which nobody uses, but like it exists, and there's some efforts to prove larger pieces of software, but I really don't know much about the subject. Wasn't it Knuth's quote that said, beware of this code, like I've only proven it correct, but I have never tested it? And so there is a danger with theorem provers, which is there's two problems, right? One is, can you actually prove that complicated piece of software works, and the other one is, how do you validate the proof? Not like in the sense that the not validate the proof, I guess, but like validate the preconditions and sort of the general, like how do you know that the thing you're proving is actually the thing that matters in the first place? Is an interesting question. For what it's worth, I don't really consider theorem provers to be super valuable. Now I know many people would disagree with this, but I'm not. I'm not really a scientist, right? I'm like very much an engineer, and I like applied research, and I dislike non-applied research. And theorem provers always seems to me like there's just a wrong ratio of the effort that goes into this versus uh, the outcome. Now, I think aspects there's like places where theorem provers could be used for good, I think, but these places have to come with a very substantial magnification, uh, multiplicative effect, in the sense that, um, so if you have a theorem prover, for example, that proves that um, a certain gate configuration on the CPU does the computation right, which my understanding is it's like a SAT problem, it's probably doable. Maybe probably this is how some of the CPU validation works. Then I think it's great because so many people get to use that CPU then, and it's so fundamental to the world. But then I think about, okay, here's a C compiler. Can you? So there's a C compiler that has a proof for this, but it's not like a useful C compiler, right? Like nobody uses this. Somebody uses it in production, but like it's not what the world is built on. Can you actually prove that GCC works? I don't even know, because this must be an effort that takes like thousands of human years, and also requires a robust model of C, which I don't know, which I guess we have to some extent. And so like I don't know if you can prove anything that's large in a reasonable amount of time. And if we normalize theorem provers, this would mean that it gets so difficult to just write code. because there's such a big difference between like the code that works and the code that works provably in terms of the implementation time. It's kind of crazy. Like a lot of like Rust is an interesting example where Rust might be the extent, like the furthest you could go in practice, to make theorem proving reasonably applicable to the everyday problems that we solve in software. So anyway, but I'm not an expert on the subject. I haven't spent a lot of time researching this, etc., etc. So take all I'm saying with a grain of salt. All right, let's try to move through this. C++ modules. I do not know the answer to this. What I know is that Microsoft Visual Studio ships. So Microsoft Visual Studio now ships support for modules in the build system as well as the compiler, which is interesting because I think it's the only compiler today that has a production build, not like a branch that you can check out someplace that supports modules. As far as build system support, I think build 2 supported modules, and I think CMake supports modules, but maybe that support hasn't landed yet. So I think Microsoft's Visual Studio is the only compiler you can use now to actually validate this. Now, I haven't played with this yet. What I have played with is Microsoft Visual Studio. So there's 2 parts to modules in C++. One is the whole framework around defining your own modules, and the other one is standard library. So the standard library modularization is actually not part of C++23. But Microsoft's compiler has a version of modules for standard library, and so I have tried this, and this was pretty great. Like it was a pretty substantial, but you can't use this, right, because it's not standard yet. But this was a pretty substantial compile improvement for some of my code that is where like the standard library includes are a substantial portion of the compile time. But I haven't tried, experimenting with modules on a larger scale or really using them at all. It's gonna be difficult because there's one thing which is, can I experiment with this? Cool. But then my time is scarce as it is, and I usually experiment with technology that I can see that either I just find really interesting, or and C++ is like a hit or miss from this perspective, mostly miss, or that I can apply. And so for modules, I think the real deal is, can I apply this? Well, I can't apply modules to any code that I work on my own, because most code that I work on my own is for other people to use, and uh, like it's gonna be more than 10 years. It's gonna be probably 15 years before I can use C++20 in my open source code. So then there is Roblox, right, the company I work at, where when can we get the toolchain that supports modules in a cross-platform manner? Well, I mean, Visual Studio 2019 will have this in a release form like next year, I'm sure. Clang and GCC, so we don't use GC, we only use Clang. But then which version of Clang? So and then CMake. So there's just like so much work in kind of trying all of this out on the production scale that I mean, we'll have people who will do this, I'm sure, but I just don't know when it will happen. But yeah, so I have played with Microsoft's compiler version of modules for standard library, and that was pretty cool. And I think you should try to check out Microsoft's Visual Studio support in general for this, because it looks like it's the furthest out across all of the other industry today. So have I tried pre-make? I said yes. State of the art is Shake build system recently with cloud feature added. Don't remember reading about Shake. What is Vulkan of meta build systems one then? So there's 2 answers to this. One is Vulkan is a meta build system by itself at this point, because you can look at Molten VK, and you can look at what's it called? There's DXVK, which does D312 to Vulkan, but also there's VKD312 or something like this, which goes the other way. So like people try to use Vulkan as a meta graphics API, but the actual honest answer that the Vulkan of meta build systems is probably going to be WebGPU, and it might actually not be too bad. I've looked at some of that work. It's fine. Their shader language situation is a disaster, but it's not through the fault of um, like it's not through the fault of people who work on the web GPU as much as through the fault of the design process for web GPU, as I understand. But so that's like a disaster. But like so in general, web GPU might be the meta like the Vulkan of. Actually, sorry, I was parsing the question the wrong way. WebGPU might be a meta graphics API, right? That might be interesting enough. So, like, if I think about what replaces OpenGL, I don't think the answer is Vulkan. It's just too damn difficult. I don't think the answer is anything else that exists in the market today, like BGFX or whatever. But maybe WebGPU is a thing. The Vulkan of meta build systems, the Vulkan of build systems. Yeah, I don't know. I don't know, man. Is scones the answer? Scones is pretty terrible. I hate scones. I don't hate Vulkan as much as I hate scones. And scones is super slow. So and scones has a lot of emphasis on being correct. Yeah, scones is not the right answer. I don't know. Maybe CMake is the Vulkan of methods. I don't know. Maybe not. Maybe Vulkan of meta build systems doesn't exist yet. Have I played with Zig? I haven't played enough with Zig. I've like compiled a couple of very basic examples, and then I actually had a project I wanted to do, which is um, to take like some code that I've written before in C++, convert it to Zig and see what happens. But the file was pretty big, so what I wanted to do was I wanted to use the Zig's translation thing from C to Zig. And my code was close to C, but then this translation thing didn't work very well, and then I kind of stopped. So I want to get some time to play with the Zig a bit more. Zig is kind of interesting, I think. I don't like Zig's syntax, it just rubs me the wrong way, so it might be hard for me to enjoy this. I don't really know why. Just like something about Zig's syntax rubs me the wrong way. But I like a lot of other things around Zig. And so I'm hoping that there's a future for Zig, but I haven't played enough with Zig to kind of really get into this and see the pros and cons and stuff like this. CMake more like Perl, but with super bad syntax. Yeah, maybe. Make files never give me issues. I like Make. People shame me for liking Make. I'm actually okay with Make. Make is bad if you care about Windows. It's like really bad, but it's actually not. I would probably characterize Make as what's a good analogy? So Make is kind of like C, if not for the portability aspects for me. So portability in Make isn't where it needs to be for a couple of reasons. It primarily has to do with shell interactions. This is like the biggest issue. Because any useful make file has a lot of bash in it, and then this doesn't work. But C is ubiquitous. C is pretty simple, but it's like complex enough to do useful work in it. C is weird. Like there's tons of stuff in C that's just like what, but it's like good enough. And so this is kind of how I feel about Make. It's hard to do really complex stuff with Make. It doesn't solve package dependency issues. It's kind of arcane and stuff like this, but honestly, I'm perfectly fine with Make. My projects, my open source projects, usually include a CMake file these days, which I never use directly because I don't like CMake, and they include a make file, which I do use directly, which is how I work on my projects. When I need Visual Studio, I usually create a project file, like a temporary project file, just add all of the source files to it, just, that's it. Yeah. I mean, make and C is a bad analogy because make is like more weird, etc. But make is not a terrible build system. Build system, I don't think. Having said this, so make files never give me issues. Most make files that you see in the wild are actually pretty bad. There's a research paper written on this, which is I think recursive make. I forget what the paper name is, but it's like it says recursive make files are bad and you should feel bad when writing them, which is true. And then I just see a lot of make files that are bad. I don't know. There is a way to write make files that works out okay in practice. And that deals with dependencies and stuff like this. It has minimal boilerplate, so this is what I use. If you look at any of my projects on GitHub that have makefiles, these are what I would consider pretty good makefiles. Maybe make is a bit like regular expressions in that the job that makes does, it actually does it pretty well. It has weird dialects that are not universally supported, but that are really important to get the work done in some cases. And then it can get pretty difficult to read a make file. So maybe make files are like in between regular expressions at C. Copper spice. I don't know what copper spice is. Do I want to know? Let's Google that. Oh, it's a UI library in C++. UI in C++ is a bad time. this is such an unfortunate failure of C++. Like this is why you see Electron apps popping up. It's not because using Electron for UI is such a great idea. It's because C++ utterly failed at getting a UI system that is actually great. There is Qt, or Qt as I call it, which I'm not an expert on. I mean, we use it in our editor. It might be Qt. Probably is the CMake of the build system of the UI systems, in the sense that it's probably the industry standard and the least terrible solution. But it's really bulky. It's like crazily big. It takes a lot of time to compile. It's just super complex. Like if you want to make a program with a single window, it's difficult. Like I don't know. But then there's nothing better than Qt. Like there's VX widgets, but my understanding is it has a lot of deep issues with this. Anyway, so like I think you can thank the rise of Electron to the general large set of issues with UI libraries in C++. Like using Electron is not a good idea, but there's just not a good alternative. So people do that. Make was too slow for my needs. It took 2 seconds to build a project of mine. Right. So if you make a make file that is good, so Ninja is faster, right? Like no question about this. But if you make a make file that is good, it can have really good no builds. It can have really good build times in general. Ninja will be faster, but make is probably going to be fast enough. So if your project is really big, then Ninja is better. So like Ninja is a great solution at scale, but the problem with Ninja is that for small projects, make is probably better because it doesn't like. I don't even know if Ninja comes with like the compiler definitions out of the gate, for example. So like Ninja is really meant as a backend for the build system, not as a build system itself. I've heard good things about Tundra. My understanding is Unity people are now using Tundra, but I haven't actually played with Tundra. But yeah, like you can no build and make can be pretty fast. It's just that um, you have to be careful when you write the make file. You have to disable, like my make files always start with the two lines that are. Let me copy and paste them. Uh, oh, is that right? I thought. Oh yeah. So like you can write secret incantations in the top of your make files. This is one example. Dash R is the important one, which disables a whole lot of built-in stuff that is like actively problematic for build times and not actually super helpful when you're trying to work. Dash J is just enables like multi-threading by default. So like Ninja is better than Make, but it's only better than Make if you use it as a backend. I find Ninja pretty hard to use like raw, right? And Make is pretty easy to use raw, depending on your problem, right? But it's like it's not too bad. But it has arcane syntax. It has issues. It's just that if I were picking between CMake and Make, absent Windows, I would like stay the hell away from CMake. But whatever. People have different opinions on this stuff. What do you think of ARM being the future of CPUs and GPUs? Oh, this is a great question that will take a bit of time to unpack. I will talk about that. Sorry, hold on. Let me. I think I jumped too far ahead. Hold on. Okay, never mind. I'm caught up. All right, Ninja, Vulkan performance blog posts. Are there some obvious limitations that tile-based GPUs have? Oh yeah, like absolutely. Tile-based designs are very interesting for power consumption, but they're actually actively problematic in some cases when, like, there are things that you take for granted in the immediate mode world, where what's a good example? Here's a super basic example. Isn't a great example. So let me put it this way. So there's two problems with tile-based designs. So one problem with tile-based designs is that somewhat interesting patterns of rendering make tile-based designs more challenging, and also tile-based designs have cost. Oh, so here's actually good. Never mind. I thought of an example. So imagine you have a render target, and then you render tons and tons and tons and tons of geometry to that render target, like tens and hundreds of millions of triangles. The immediate mode GPU requires constant amount of memory, short of like however you are generating this geometry. But like, let's say you are generating this geometry by instancing a single mesh, like 1,000 times or like 1,000,000 times. The amount of memory that you need in the immediate mode GPU to process all of this is reasonably constant. You need the render target, right, of course. But let's say you're rendering a 1080p, and let's say you're rendering a single mesh, and you're rendering million instances of that single mesh, and that mesh is like 1,000 triangles. So you're rendering a billion triangles. What you need in terms of memory is you need a buffer for the 1080p like frame buffer, plus you need a million instance descriptors, which you need to store transforms and stuff like this. So maybe you have like 64 bytes, maybe you have 100 bytes. So maybe you need like 100 megabytes of instance memory data. What the tiler needs to do, what tilers, there's two types of tilers that are common. One type of tilers runs your vertex shader for the entire geometry that you are submitting, stores every single output like attribute of the vertex shader in memory. Um, and then runs the rasterization, runs the binning pass that looks at the triangles, like classifies them per tile, etc., 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 and then runs rasterize, runs the fragment shader. And then there is the second class, which runs just the position output vertex shader that I was talking about earlier, then runs the binning, etc., etc. All of these require memory that is proportional to the number of vertices that you need for your scene at least. And in the first case, it requires memory as proportional to the number of vertices times the amount of memory that your vertex shader needs to output data, which for our scene of like a million instances of 1,000 triangles is on the order of a billion, right? How do tilers deal with that? There's two ways to deal with this. One is to have a really, really big buffer for this geometry, plus use interesting compression techniques, which tilers do. But this buffer runs out, and you will not have this buffer measured in gigabytes ever. The other thing that you can do is after this buffer overflows, you can flush the scene, what's called. So finish the rasterization pass and then start it again, like store the results to memory, then start it again, and then continue rendering. This flush has many problems. One is it's crazily expensive. I mean, not crazily, but like you have to store the whole thing to memory and then you have to read the whole thing to memory. So like it's not great. The other one is it's expensive also for reasons that like the tilers are often not designed to make it cheap. And so it just can be expensive just because, people haven't thought about this. And then also in some graphics APIs, I won't name names, but in all modern graphics APIs, there's failure modes where the graphics API just doesn't work if you have too much geometry. And I won't name names, but this is a problem in all modern graphics APIs, and the severity of the problem varies by the API and the vendor, and some other configurations of the scene. But like you can get your rendering to be broken on all modern APIs. So that's like a big issue, right? There's like a performance cliff, so you render like a million triangles, things work great. You render a million and 5 triangles, suddenly the buffer overflows, you have a scene flash, like it's not good time. All of this is hardware dependent, all of this is unpredictable, like it's pretty bad. So this is one problem with tilers. And the second problem with tilers is just that this whole tile shader business, etc., that I talked about this, is just a more complex programming model. And so on desktop, you now see designs both from NVIDIA and from AMD that use tiling as an acceleration technique for rasterization that is transparent to the user. And that's pretty cool. Like that might be the best balance between the two, where, you try to use styling to the extent that it saves bandwidth, but then your actual architecture still supports immediate mode. My understanding is Qualcomm chips also support this duality, but they support this on a more they support this in a different level, so it's not like as good, I would argue. Maybe it's good, I don't know. So anyway, there's problems because the programming model is just more complicated, and so if you want to run your code in an optimal way, in an optimal performance, it's just much harder to do this. So the best of both worlds, right, is to have memory that's just really fast. For example, there was an interesting difference between. Can I talk about this? Some of this stuff is publicly documented. I don't know to what extent. Let's just say what you deal with in tilers. Okay, let me put this in abstract terms. What you deal with in tilers is this. There's the main memory that has bandwidth that is comparatively small, let's say like 10 gigabytes a second on a mobile chip. And then you have the styled memory. It's still memory, like it's still memory somewhere on die. It's small. It's like, I don't know, a few megabytes maybe, but it's like really fast. It's like 10 times faster. So it's like 100 gigabytes a second. Um, Compare this to the design where all of your memory just has 100 gigabytes a second of bandwidth from the GPU's perspective, which is how which is how dedicated GPU memory works, right? And in terms of integrated, it depends on stuff. But like this second world is much better from the ease of use perspective, and also from the kind of getting good performance out of certain interesting rendering techniques, etc. The problem with this world is that fast memory costs more, and fast memory is more power hungry. And so this is why if you work with embedded space, it's like not a great trade-off. But all other things being equal, like if power and cost isn't a big deal, I'd rather just have memory that runs at like hundreds of gigabytes a second, from the perspective of the graphics card. But yeah, practical designs these days, I think, are immediate mode with reasonably fast memory plus a secret sort of hidden tile cache, which is how both NVIDIA and AMD do this these days. Okay. Why don't we have better control over image presentation synchronization piece? Oh my god. Yes. Um, um, So this is an interesting question. I might go back. Let me go through the rest of the chat, just to see maybe there's like topics outside of the things we've discussed that are interesting to talk about as well. I'm not an expert on this either, but there's some things I can talk about this in this context, I suppose. If you're writing render for normal GPUs and tile GPUs, will the render pass solution slow performance than normal GPUs? I mean, the answer is no, but it's more complicated than this. The answer is no in the example that I've just sketched out, but there are other examples where, to take full advantage of the Tyler GPUs, the Vulkan render pass APIs are just insufficient. And there are other examples where using them constrains your renderer too much, just because of how the API is structured. Like you have to recreate render passes, you have to express, like you have to recompile shaders, you have to, so if you want to change your render pass configuration dynamically, which you want to do for various performance tuning reasons. So, like, the way I would describe Vulkan model is this. For most interesting things, it's just not sufficient. It's not expressive enough. For example, Apple has examples. Like Apple has metal examples for cluster deferred shading, which do kind of light binning, and then I think it's like so here's what you can do with metal image blocks. So in a there are other designs for all of this stuff that have different performance characteristics, but here's an example design that is actually rather popular, was rather popular in console renderers for the previous gen. You render the depth buffer, just the depth buffer, maybe a small color buffer, but then you run what's called a tile, sort of tile classification, but it's more than that, but whatever. Let's just call it tile classification pass. It's not quite correct term. I'm blanking on the exact correct term. But what this pass would do is it would split your screen into small tiles, let's say 8 by 8 pixels. For each tile, it would, based on the depth information in the tile, so it would aggregate this like do min max. And then select the light sources that overlap this tile and can influence the depth range. So this would be tile-based culling, right? Tile-based. I guess maybe it's just called tile-based light culling. Um, what you get from the result of this is that for each tile that's 8 by 8, you get a list of lights, or for example, a bit mask of lights that you will use. And then you do a second geometry pass, where in your fragment shader, you look at the tile, you look at the list of lights, and then you do a loop through the lights, and then you apply lighting. This is a fantastic lighting architecture. It has downsides. One downside it has is that if your depth range in the tile is really large, then the effectiveness of the culling stage is not good. But it's actually rather simple to solve this problem for some cases. For example, there is a super interesting solution that's really pragmatic, where you just you can split the depth range in two. So instead of just having one list per tile, you can output two lists per tile. And this deals really well with some cases where the naive solution isn't great. And this has like massive, like I really like this design. So there's things around this design that are not perfect, such as handling of transparent objects, but it's like a fantastic way to do lighting. There's more modern ways to do this where that are called forward plus, where you build a 3D grid, which is how Futures by 3 works for Roblox. But they have downsides. There's ways to combine forward plus with this thing that are just absolutely great, where you do a forward plus, so you build a 3D grid, but you use depth information that is pre-built because you want to do depth pre-pass anyway, because it just saves shading costs massively. And when you build your forward plus grid, you use the depth information to do a more accurate tile classification around the geometry. And this really helps in some cases. For example, forward plus, one big weakness of forward plus performance-wise is that let's say you have a wall, and let's say you have a light inside the building. Super common. Let's say you look at this and you're reasonably far away. The way forward plus works is, I'm sorry, for people who don't know what forward plus is, this will make no sense whatsoever, but you can Google it later. But forward plus works by building like a 3D voxel grid or sort of voxel grid in frustum space, and it builds these light lists per tile, per like voxel. But if your camera is far away, these voxels can be rather big depth-wise. So what can happen is you can have voxels that align like this, like that start before the wall but end far, like way after the wall. And these voxels will accumulate lights that you don't care about processing for these pixels because they're like behind, right? But you don't know. And so if you have depth information, you can do this classification using the depth information that you have per tile, but still building the 3D grid, and that's also great. So anyway, there's like so many nice things about all of these techniques. But notice what has to happen here. You render depth, you do tile classification or whatever, and then you render geometry. Well, what this says on the tiled architectures is that you have to render the depth out to main memory, then run a compute shader that reads it, etc., and then run a geometry pass. Vulkan cannot do this at all without, flushing results to memory. Metal can. You can look it up, like Apple has an example of doing this. It's not too difficult. So what I would say is that the Vulkan render pass design has two very bad features. One is it makes life actively difficult for people who don't care about tilers, right? Two, it doesn't solve the tiler problem well. Like the things that you can do in Vulkan that are like around render passes, some of them don't work. Like some of them, you write code that should work, but then driver doesn't do a good job at doing this, and like it doesn't. An example of this is a custom multi-sampled anti-aliasing resolve. It's like rather difficult, I think, to find a driver where this works. Custom being the imperative term, like the fixed function thing works, right? So it's not good enough for tilers, and it makes life actively difficult for people who don't use tilers. So it's actually a really bad design. And like people who, without naming names, people who I've talked to from Kronos who worked on this design, they agree. like it looked really good. It's really hard to assess the value of design before going through the whole process, right? Because like have to make a design, have to agree with different IHVs of whether the design is implementable. Then you have to ship some version of software that works with this. Then you have to talk to people who make games to actually use this. But to make this work, like you talk to like a company who is doing AAA grade like lighting rendering engines, like has an in-house engine, and they're like, hey guys, can you like spend a bunch of engineering time to figure out if your engine can be ported really really well on this API that doesn't exist yet, on drivers that don't exist yet? Like, it's just really hard to do this kind of stuff. So I think it sounded like a good idea at the time. It's not a good idea. So um, not to say that metal image blocks are like superior in every possible way, but metal image blocks have two characteristics about them. One is if you don't care about tilers, you just don't, or if you care about tilers but you don't. Render passes by themselves aren't like that bad. Metal has a good version of them. Subpasses are subpasses, input attachments, like all of this. It should just never have happened. So if you don't care about tilers to the extent of wanting to write custom code to support them, Metal has a really good balance between the complexity of the API versus the performance characteristics of the code that you write. And if you want to take advantage of the Tyler hardware, Metal gives you the APIs for this. Whereas Vulkan makes it difficult for you if you don't care too much, and makes it impossible for you if you actually care. So, um, all right. Would you prefer if GPU vendors made low-level APIs versus all? I don't actually know. So okay, here's the deal. I would actually be fine if there were like three graphics APIs, NVIDIA, AMD, and Intel, that I would have to use. And if every API was cross-platform and cross-architecture, I think it would have been a possibly better outcome than what we have today. But this would never happen this way, right? So if NVIDIA made a custom API, it would only work on like Windows, and then you go to Android where you can get an NVIDIA GPU, or you go to Wii, which is it? Oh, sorry, not Wii, Switch, right, which uses NVIDIA hardware. Actually, Switch would probably work out because I think on Switch, NVIDIA owns a large portion of the software stack. Um, or like you go to Linux, or you go to some platforms with the same hardware, and they just don't have this, right? Or like you have AMD make this API, and then you have Xbox and PS5. Would they all use this? I think the answer is no, right? Or then you have AMD, and then AMD ships a new graphics card. Will they ship a new, like, will you have to use the new APIs? I think this is the difficult part. I think the world with vendor-specific APIs would be better, but if these APIs would be cross-platform and cross-architecture, and I think both of these are problematic because of different reasons. So I'm not suggesting that I know a way out, right? I'm just saying like the situation that we are in right now is bad. I'm not suggesting that I know the best way how to fix this. Like, I think it would be great if there was one API that was like useful on all of the platforms. Vulkan could be that API. Vulkan has a lot of issues, so in my ideal world, it would be an API that is better than Vulkan. But in theory, right, you could imagine Vulkan working on all of these different platforms, and I think that would be a better state of affairs than what we are in today, but that would also not happen. So like, I can imagine multiple different solutions to the problem that we have today, but I don't know that deploying the solutions is possible, which is why I think maybe this is a maturity problem. Like, maybe in 20 years the pace of innovation in the space slows down and there's more sort of stabilization in terms of APIs and feature sets, that people look at all of this and are like, can we stop doing this crazy thing? And maybe in 10 years it would be. um One other thing to say about all of this is that you can also look at this perspective from the new world of, like more than half of the mobile games are built on Unity. A lot of the, I don't think it's more than half, but a lot of the games on consoles and PC are built on Unreal. 10 years ago, so today there are still many custom engines that are being used, and in AAA productions, including, right? But if you looked at this space 10 years ago, then I think there was probably 5 times the number of in-house engines. I think a lot of the in-house engines, there's a few things that happened. One is a lot of the studios that didn't go out of business, right, just found it more difficult to justify investment in their own technology versus licensing Unreal. The other thing that happened is Electronic Arts bought a bunch of studios and then forced them to use Frostbite. And then the third thing that happened is there was consolidation in other parts of the industry. For example, Ubisoft got a bunch of big studios, and then I think there was a lot of push internally there to use some internal technology stack, like across different game franchises. So throughout all of this process, right, we just have way fewer custom engines. And so, from a certain perspective, none of this matters because this only matters for people who don't use Unity or Unreal. And from a certain perspective, the number of these people will dwindle probably over the years. But it makes me sad because there is a lot of use for custom. Like, there's so many ways in which a custom engine could be superior to Unreal or Unity or any other engine. And if it was easy to make them, like, it would be a more interesting world to live in. It's just too freaking difficult. VKFFT looks good as an example of Vulkan compute. Have not looked at VKFFT. Vulkan, as a compute API, Vulkan is not great at all, but is better than Vulkan for graphics. Like, it's just like much less complicated, right? But it's still hard. So ARM future of CPUs, GPUs. Sorry, we'll talk about this. I want to get through the rest of the questions just to see the landscape. There's a proven microkernel extended binary treating compilers black box. Yeah, so like, here's two things to say about this. One is, again, look at the production systems and ask the question, right? So production systems run Linux, production systems run Windows. Like, it's probably crazy amount of effort to like to actually prove that all of this code works. The other thing I want to say about this is that assumptions change all the time. So here's an example. Until 2 years ago, the idea that okay, until a few years ago, the idea that in this code you can actually know the value of the entire data array after calling this function. Even if it was understood by some, it was definitely not understood by the industry at large. What happened in the last couple of years is that the vulnerabilities around side channel attacks, like Meltdown, Spectre, etc., were discovered, What does this do to the? So proof of correctness is a bit different from the proof of like security, right? But so like let's say you're looking at the interpreter of so a good example is Linux has a thing in the kernel called BPF, which stands for Berkeley Packet Filter, but has little to do with Berkeley Packet Filter these days because it's a virtual machine that can execute code in the kernel space, but that code is safely sandboxed. And WebAssembly has similar characteristics. So it seems very tempting to say that once you make a formal proof of the fact that this sandbox is secure, as in you can't access memory, like none of the implementation of the virtual machine can't access memory outside of the one that's given to it, right? It seems tempting to say that once you have the formal proof of the implementation of that thing, then you can deploy that thing and have the kernel be secure, but that's just not true anymore, right? So what happened there is that some of the axioms, right, that a formal proof engine would probably follow were broken. Like the axiom that in this code, data index expression is executed only if index is less than 5. This was broken by the realization that the speculative execution kind of leaves a side channel. And so this is like I think there's a bit of a like having a formal verification is much better than not having this, but there's also kind of a sense in which it's not enough. Anyway, but yeah, I don't know. I just don't see this as a big thing. From the combination of the practicality and kind of the increased development cost and stuff like this, right? So like you're saying 10x dev cost. So I again, I'm super ignorant on the subject, right? You can treat everything that I'm saying about that specific subject with like a giant bag of salt. But let's say this is true. Let's say it's 10x the dev cost. It's kind of crazy, right? In the sense that if you look at the Linux development, for example, um, Linux is already like there's already a monumental amount of effort that goes into Linux. Do we have 10x, 20x resources in the world to make Linux use that? I think the answer is probably no, and I think the solution is probably that Linux shouldn't be as damn complicated as it is today, and then it's okay, right? So like, can we build a world on software that's simpler and has formal proof? So maybe we can. I just don't see how this would come to fruition, so I'm not as excited about this. I compare this to, so I think fuzzing did way more good for the world versus theorem provers in terms of ensuring software stability. Fuzzers don't give you a proof, but for a large class of software, they give you such an easy to deploy, such a powerful tool to gain so much more confidence about this than you used to have that it's just better in some way, in my opinion, right? It's not the ultimate solution, but if you compare this, it's like yeah, so Coq is an example of like a theorem proving system. It is an interesting view on the computation, right? It's just I feel like it's not really compatible with how the world today works, and so other modern issues with 3D rendering that are a big hang up with performance. Are there any super complex problems you're trying to figure out? I mean, not me personally. I've distanced a bit from the 3D rendering, but for the world, like, I mean, there's no shortage of them. You can look at all of the ray tracing stuff, which is really, really difficult. Which boils down to, we after decades of rasterization research, we don't have great ways to do reflections and shadows, or global illumination. Ray tracing provides a way to do this, but it's so difficult to build a good API for this. It's so difficult which neither of the existing ones APIs I think are good. It's so difficult to build a good implementation of this, which is clearly shown. You can look at the ray tracing performance benchmarks for NVIDIA versus AMD hardware, and it's just so clear that there's so much work left to do there because there's such a big disparity today between these. So yeah, I mean, there's many problems in rendering today that are really not solved. I'm not the best person to talk about this, but um, I believe Angelo Pesce did a presentation about this on Digital Dragons recently, so you can listen to him. Also, Johan Anderson did, I think, two presentations about open problems, I think, in real-time rendering or something like this it's called. I think he did two presentations about this a few years ago. I think the last one is probably from 3 years ago or so. I think the first one is probably from 5 years ago. And I suspect that for all of them, we still haven't solved the problem. So yeah, like there's still a lot of really hard problems to solve in rendering. Make as Haskell as Ninja C. Huh. Make is not. Haskell has a crazily strong theoretical background, right? So I would probably equate Sconce is perhaps closer to Haskell. In that Sconce is really trying to be Sconce is kind of failing to be correct. So anyway, whatever. Let's analogies. It's like a slippery slope. Make and FreeBSD ports, yeah. So I haven't used FreeBSD, right? I used Mac and Linux, and on Mac and Linux, Make works pretty great. But I suspect that FreeBSD doesn't have GNU Make, and GNU Make has pretty useful features that the non-GNU Make doesn't, the BSD Make doesn't. And that's in general. So this is I think how a lot of the systems fail. So maybe that's a good thing to talk about because I like how today we have a lot of themes that seem very different, but they're actually really close. So let's talk about this problem, right? So there is a make language. You can write a make file in that make language, and then you can run it. And then there's an implementation GNU make, and there's an implementation BSD make, and these are not compatible. Why are there two implementations? Like, I think the main reason is licensing. From what I understand, FreeBSD people really don't like GPL licensed software, and so everything that's GPL licensed is being rewritten. And then GNU Make, of course, originates. I'm sure Richard Stallman wrote this, and if he didn't, like somebody from that era did, and GPL was the thing that time at the time. But that's such a pointless thing to split hairs about. Like, there's no reason why, right? There couldn't have been just one make. Similarly, if you look at all of this graphics API craziness, it's kind of the same story. If you look at graphics drivers things, it's kind of the same story. Like there's two AMD drivers today. Oh, sorry, three I think AMD drivers today for Linux. None of them shares any reasonable amount of source code with an AMD driver for Windows, with any AMD driver for Windows. There's a bunch of different AMD drivers for Windows, and they share varying amounts of source code within themselves. And like this just makes no freaking sense at all if you think about this from the first principles, right? Like there's explanations for all of these. Somebody's asking, isn't Apple's make BSD make? I'm actually not sure. Maybe it has some GNU extensions, but like somehow I didn't really have a lot of problems between Linux and Mac. Anyway, like so from the first principles, all of this looks like stupidity, right? Like there's no reason why this has to exist, and this is there is something kind of deep about this. There is this view that people have around standards and multiple implementations that I kind of really disagree with because I've seen it play out so poorly in practice. If you look at the landscape of the C++ compilers, there's like several different ones. There's three major different C++ compilers, four if you count Intel, which has use in like some domains. They have different behavior. They have different language feature set support. There's human time that's just wasted. Like There's people who work on modules implementation in every one of these compilers, and this is just wasted effort. Like there is no use. And so on some level, competition makes sense, but on some other level, really, world would have probably been a better place if there was one. You can look at Rust, and oh my god, Rust solves so many problems that C++ has, not because it's a better language, it has nothing to do with this, just because it has a different software mentality. If I find a problem in Rust standard library, the way to fix this problem, like a performance problem, let's say, right? The way to fix this problem is to submit a pull request to the Rust GitHub repository. Once it lands, which, like code review, like who knows, but once it lands, it will be available in the next Rust release. It will apply to all Rust programs on all architectures, on all operating systems, on everything. If I find a performance problem with STL, these days, thankfully, I can actually submit a pull request to all like dominant implementations because Microsoft open sourced that one. Thank you, Microsoft, for that. But there is 3 implementations. And so, like, to actually fix the problem, I have to profile all of them, and they actually have different implementations, so their performance characteristics are fundamentally different. But if the problem happens in all of them, I have to submit a similar code change in very, very different code bases that have different review processes. It's just like so much friction to do this. Let's say my problem was not with the like STL, and it was with the compiler. I can't even do this for Microsoft. Let's say my problem was with STL implementation, but what it required was not an implementation change, but it's an interface change. Let's say there is a new function that could have different semantics that would have just dramatic performance implications. Or let's say there was a new container. There's so many examples of this in STL. How do you fix this in C++? Oh my god, you just don't. Like, it takes years. You have to be involved in the standardization process, have to submit papers. Probably it's going to get rejected. If it actually gets submitted, like, it's so much work. And then, let's say you have a design for the new container that fixes performance issues design-wise. Let's say the paper gets through. Now there's going to be 3 different implementations of this new thing in some future versions of the STL done by different people. Are they all going to be optimal? Like, no. Like, just no way, right? Microsoft recently implemented a really good set of optimizations for printing floating point numbers in their C runtime, C++ runtime actually. It's not applicable to all functions yet, but like once it will be, is it the same performance that you get, or behavior really, that you get on other platforms? Like, no. So this is just a terrible way to develop software, right? There's so many places where the standard plus independent implementation model works really well, and there's so many places in software that it just leads to pointless differences in APIs, pointless differences in performance, pointless differences in behavior. Like, all of this doesn't have any use. And so the make duality is like a perfect example of this. There's no reason why this has to be the case. Both FreeBSD and Linux support the same shell. So the shell code that you run in your make is going to be compatible. I don't think it's probably a different shell implementation. I don't actually know this. Anyway, so there's no reason for this difference. The reason is completely pointless. It's historical. It's like license based, but like there's no like fundamental reason why this has to be the case, right? And so this drives me nuts about like about kind of the state of the modern world. This is part of why I do the open source work that I do. Like when I started Mesh Optimizer, so there's a bunch of different engines that do some of this work proprietary. There's no open source implementation for anything. All open source implementations that are there are made by people from academia. That they don't work on real game. Like, it's just a sad state of affairs, right? And so part of the work that I'm doing this because it just drives me nuts, and so I'm trying to help fix this. But all of the ways in which this problem is fundamental are like all of these problems in the lower level of the software. They're like really hard to fix, right? Like, why do we have so many different kernels for the operating systems? Like, I don't know, it just makes no freaking sense. I mean, again, it makes sense because of the historical implications, but from first principles, you look at this. Not to say that there has to be one implementation of everything. It makes sense that we have different programming languages, right? Like, sure. And it even makes sense that we have different programming languages that are close to each other because they have to compete on ideas, right? So, like, it makes sense that Zig is different from C. It makes sense that Go is different from Zig, like Go has garbage collector, right? It makes sense that Go is different from Rust. It makes sense that Rust is different from Zig. Like, but like, why is there different implementations of the same ideas, etc., etc., etc.? So there's so many things that are fundamentally broken around kind of software development, and a lot of the graphics problems come from that, right? You don't want to know how many implementations are there, so you have, again, going back to this AMD problem, you start from HLSL source, which everybody under the sun writes shaders in unless you're an enthusiast in academia, or unless, I don't know, whatever. Like any like serious like AAA, AA, I don't really care. Like, people write shaders in the shell cell, which doesn't have a formal spec, by the way, but that's a separate problem. And then there's this AMD low-level instruction set that is actually documented. You can look up online AMD GPU ISA for every different architecture's documentation. How many different compiler stacks do you think that go between like the HLSL representation that like humans write and the ISA that GPUs consume? You don't want to know the answer. It's like, seriously, you don't want to know. Um, but it's like, wait to me. It's not one or two. It's not three. It's not five. It's not even five. It's like, is 10 a good number? I know there's more than five. It's probably between 5 and 10. And there's no reason for this, but it's kind of how the world works. Okay. Yeah, so Zig C++. I'm pretty comfortable with writing C++ code because I have a way how I write C++ code that's minimally problematic. I'm used to all of the Vulkans, like, I know how to do this stuff. Like, I've been doing this for decades now. So I'm actually very productive in C++. I make very, very few mistakes because I write my code. I make logical bugs, like, everybody does, but I try to write code in a way that it's obvious that the code works from the memory safety perspective, etc. And so I don't have a huge problem with this. But C++ falls short in many different ways. Like, so the standard library is pretty consistently terrible. There's many different compilers, which is painful. And then there's compile time, like all of this stuff. And then there is the evolution process, right? Which is just like every next version of C++ adds a couple of features that I like, adds a ton of features that I don't like, and isn't usable, like the fragmentation problems that I've just talked about, etc., etc., etc. So Zig is much simpler and has much better development model, and etc. So in that sense, right, the way I think about Zig is this. So I write code in C++. I will continue writing code in C++ for the next like 5 years. But then, assuming I still write code after this, which I think will be true, just because I like solving problems, do I continue writing this code in C++? The rate at which the current C++ development is going, every next year I feel less happy about the state of C++ than I felt the previous year. Like, this is not an exaggeration. Just from the overall, like, direction, community perspective, ways in which the language is fragmented, ways in which the standard committee just doesn't solve the right problems. Um, Modules were the only important feature of C++ 20. You could argue modules were the most important feature of C++11. Why does it take forever? Like, build systems are crazily important. Package management is crazily important. They now have a working group to work through these issues. I have no faith in them doing anything in the next decade, like shipping anything in the next decade, which is, again, not to trivialize. Like, if anybody is listening to this and is on the committee, I know what you're going to say. I recognize that this is hard. I have no interest in being involved in this process for multiple reasons. And one of which is that I just disagree fundamentally with how this, like, again, like, look at Rust. This is how people make progress. This is how people get things done. It's still really hard. It still takes a decade to get a language out. But the fundamentals of how this process works are just superior. Like, there's no question about this, and the results show themselves, right? Like, but then I think, okay, what's the next language for me after C++? Is it Rust? And this is where Rust inherits some of the problems from C++ that kind of makes me a bit down on the language. And Rust community is really welcoming, which is great, but there is way too much zealotry going on, which I don't like. Like, all of this Rust evangelism, like, it drives me completely nuts. Like, all of this rewriting Rust for the sake of rewriting it in Rust. Like, so there's a bunch of stuff that I don't appreciate about Rust from the ecosystem perspective, and there's a bunch of stuff that I don't appreciate about Rust from the, like, values, pragmatism, etc. perspective. The big ones being compile times. I know they're getting better, but every time I tried Rust in the past, like, this was actually physically painful for me. Not that C++ is great, but in C++, C++ is actually, like, much better if you write code really carefully. And in Rust, my impression is it's much harder to do this. But, like, it's kind of the same deal, right? Even if it's exactly as bad as C++, I really dislike this about C++, so why would I, like, Anyway, so maybe Rust is still the future. Rust has good properties, but there are other things I don't like about Rust that are fundamental. Like, it's harder for me to write code in Rust from the friction perspective, for a number of reasons. And maybe I just get over this, but this is why I was looking at Zing, right? Not because it's necessarily a transformative experience compared to C++, if you use C++ carefully, but because it could have feature that I could get behind, whereas C++ today does not have a feature that I can get behind. So there's that. Rust has a better chance probably because, Rust definitely has a better chance as the language. Every person decides for themselves kind of what they want to associate with, but Zig could be a good replacement for C. Like, Rust is probably a good replacement for C++. Rust is a terrible replacement for C, and so in that sense, the question is, what's the next C? And Zig right now is the most promising candidate. So this is how I would summarize this. Oh, all right. 4 plus render versus tilers. Are there any planned extensions that would make working with tilers more reasonable? I can't talk about the things I know. But even the things that I know are not crazily exciting. So, like, don't get your hopes up. I think Vulkan has this really hard problem. It has, like, an identity crisis, right? Because it's like a thing you should use everywhere, but also it's a thing that should work really well in this situation versus that situation, and it's just, like, really difficult. And it's getting less and less manageable with the amount of extensions that is getting added, etc., etc., etc. So, anyway, but yeah, I can't talk about anything I know publicly. Somebody is thanking me for QGrep. I'm really happy that it works for other people as well. I haven't dedicated too much time to the project lately, but it's pretty complete in the sense that like I used it daily. I fixed everything I don't like about it, etc., 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 and it's pretty neat. It's not the thing I usually do. It's like not a library, and there was a bunch of cool stuff that I had to work on when working on this. So that was pretty fun. I noticed just now that we are closing in on the 3 hour mark, so we'll have to finish this in 15 minutes, which is enough time to talk about one thing in a reasonable amount of depth. But the good news is that I got through basically all of the questions. I skipped one about ARM, uh, which do I want to talk about? Let me go back. There's a couple more questions around language stuff. Uh, Sorry, where was this question? Ooh, hold on. Oh, right. R being future of CPUs, GPUs. So I kind of want to talk about that. Uh, Not physically possible to improve C++ solution process. Yes. I'm not saying there's a way out. I'm just saying I don't like it, and I think there is physical proof, like actual proof, that it's a problem. Like not the language. Language itself is bad for many reasons, but I think there is data proving that the way how C++ works, both from the language and from the implementation perspective, hurts innovation to the point where really important things that had to have been done 10 years ago just haven't been done and will not be done in a reasonable time frame. So I think part of the problem is just that there is not a core group that works on C++, right? There's like 300 people in the C++ standardization committee or something like this. Like you don't get things done this way. Rust's model, I think, might be the best balance between kind of being able to make important decisions, but also having community be heavily involved in them, because they have an RFC process, but there is veto power, to my understanding, that the group that works on the language has, and fundamentally they make the call, and I think this is the right model. Do you think we'll ever see C++ do a hard break with compatibility for older code to clean up language? So C++ does this, but it does this, it's like, oh my god. They deprecated and removed now std random shuffle, which randomly breaks, like not very significantly, but it randomly breaks programs and it randomly makes them harder to fix. Did deprecating and removing random shuffle serve a purpose? Like, no. So I think the unfortunate reality is that things that they can remove from the language are non-essential, but they want to clean the language up, so they remove things that are not very essential, but this results in pointless breakages. And so like I think the important things in C++ are really hard to get away of. I'm excited, I'm like low-key excited, I guess, about modules, and so I wonder if there is a world in 20 years where like you can deprecate the old compilation model essentially, but even that will probably not come to pass because there's so much software that fundamentally depends on this. Like it's too little too late, I think it's going to be super hard. One thing C++ doesn't do and can't do is what Rust started doing, which is epochs, which is a great idea for language evolution. It only works if you have a strong module system and strong ideas of kind of interface level compatibilities. If C++ shipped modules 10 years ago, maybe today we could be starting to talk about epochs. And maybe it would be possible to say my module's interface has to comply with C++ 11, but the interface is really simple. My module's implementation can use C++ 23 or whatever, But and C++23 makes a few daring things that make code more difficult to port, but you don't have to. And all different language kind of versions interop in a good way. Today, the way how this works is very fragile, and there's so much stuff that leads to the interface boundary, and it's just like, ugh. Anyway, like no, nothing good will happen. There's really basic things about the standard library as well. Like you have to buy into a new language feature to use. So, like the big problem, for example, is this: to use std optional, you need C++17. To use C++17, you need C++17 compiler. Can you implement std optional using C++11? Yes. But it doesn't help you if you have a C++11 system. And so there's so many issues around this whole process that are broken that I don't think it's salvageable at this point. Um, Hopefully the people steering Vulkan doesn't go the same just at stuff part, which should be avoidable given the prior experience for OpenGL, you'd think. So it's complicated, right? Again, like I don't want to trivialize the problem. I think everybody who is listening to the stream should understand that whenever all of these things that I say that say something is really broken or fundamentally wrong, I think mostly these statements are ones that people who work on this stuff would agree with. It's just that there is complex reasons why this must be true, and there's complex reasons as to why the state we are in is the state where we are sort of making forward progress, and it might be better than doing nothing. So here's an example. Vulkan now has an extension for stream output. It's called X transform feedback. Stream output is widely recognized by everybody who I've talked to on the standardization committee, on the GPU vendors, like everyone thinks it's a bad feature. It's not like crazily problematic, so it's not like a giant disaster, but it's like a bad feature. Why did Vulkan add an extension for this, you may ask? Well, turns out that Direct3D has shipped this feature in Direct3D 10. Then this feature became pointless, mostly, in Direct3D 11 with the introduction of compute shaders, but nobody ever removed this feature. Unfortunately, it's still there. Is it still there in D3D 12? I think it might be. I think it is. To run games on Linux that were built for Windows, now there is this Proton thing that relies on VKD3D or D3D DXVK, whatever it's called, to translate from D3D 12 to Vulkan. Turns out like Wisher 3 or something like this requires stream output. And this is how legacy carries through, right? So Microsoft hasn't removed this feature from Direct3D, which means that this feature is still used by people who could not use this feature, but they use it because, it's there. And now it has to make it to Vulkan, because if it doesn't make it to Vulkan, Wisher 3 doesn't run on Proton. So like, is it a bad decision to add this extension? Who knows? Because it's a bad extension, but like, it's necessary. And it's really hard to navigate this space because of things like this, right? Yeah, so I hope that at some point there is a new version of Vulkan or something that just cleans up this mess, but it's not looking great right now. It's still much better than OpenGL. I would use it in a heartbeat over OpenGL for a production renderer. It's just there are things in software industry that are great, and there are things that are good enough. Vulkan is good enough, but it is not great. And so it just saddens me when the industry settles for good enough, where an alternative could be great, and a great alternative isn't out of the question, and it isn't physically impossible or implausible, and it isn't beyond reach, right? It just isn't there. Um, Do you think std should be part of the core language? Found weird including std languages in the language core. My ideal model of the language evolution would be one where there is a separate standard library that is there is a canonical implementation and everybody ships that instead of like whatever they come up with. It's open source, etc., etc., and there is some distance between the language, the core language, and the standard library, so that there can be a compiler that implements C++11, but you can use the standard library that is C++ like 25 or whatever, right? There are many things that prevent this. One of the things that prevent this is that for whatever reason, people decided that shipping a DLL implementation of C++ on operating systems is a great idea. So on macOS, you cannot use std optional, which is a templated class, you understand, but you cannot use std optional, or you can use some members of std optional unless you stop supporting macOS versions before like 10.14 or something like this, which you cannot do if you're shipping a Mac app. And so, like, can you use C++17 on Mac? The answer is no. You can't use a lot of parts of that because of the linking model. So it's all broken fundamentally. Like, it's all a disaster. But yeah, I'm not happy about two things. We will never get to the ARM question. I'm not happy about two things around C++. One thing is, I think parts of C++ that get standardized as a standard library should have been core. Like std array is not a good idea. As like a very, very basic example. Std optional is also not a great. Not std optional, like there's problems around this as well. Anyway, but then the big problem is that the standard library is moving slowly, and there's many different versions of this. So anyway, what things are great? Don't want to go into this. There are few and far between. But like again, in the graphics CPI context, I don't think Metal is great, but it is way closer to great. There's a couple of things about Metal that are just bad design choices, I think. Again, I think industry agrees with me that Apple made that. If I were at Apple, I understand why they made them, but at the same time, it's like a broken thing. But by and large, I think Metal is as close that you can get to great as graphics APIs go, unless you go into the console territory. But when you go into the console territory, you start getting really attached to the hardware in question, right? And so there's questions about interoperability and all of that. But I think Metal is as close to great as far as reasonably open graphics APIs go. But like, of course, Metal isn't usable anywhere outside of the Apple ecosystem, so it's great, but it's not useful. All right. So I want to. Let's just finish this. So there was a question about the presentation stuff. Which was like, why is presentation so broken in the modern world? So it's hard for me to fully answer this question because I don't understand all of the moving pieces well enough. But what I would say, without getting too much into this, is that I think this is an example again of there's many different pieces, many different moving pieces, and there's competing priorities kind of for all of the different parties involved. And also this is where all of the presentation, the best presentation API that I'm aware of today is the XGI. And I think the reason why it's the best API has to do with Microsoft having the best understanding of the of what it takes to ship a desktop operating system in general. but also having a strong notion in the kernel of like, we have a graphics subsystem, we are trying to design it in like a good way, etc., etc. But I think fundamentally the big problem with presentation is that there are many parties involved in kind of making decisions. There is the game developer who wants features that you may not expect if you don't have the game development context in mind. To give you a very basic example, John Carmack, I think, argued for this billion years ago, as he usually does. And it made it into Vulkan as FIFO relaxed presentation mode, but very few vendors support it. And it doesn't play nice with the DXGI composition model, actually. But there is a thing that people used to do on console all the time. I've personally implemented this in one of the engines I was working on PlayStation 3, and it took me like a day to implement. The graphics API didn't natively support this, but it had enough functionality to be able to implement this on top of this because it had low-level access. And the functionality goes like this. So in the era before G-Sync and stuff like this, right? Before variable rate refresh rate, which I'm not an expert on, I don't fully know how it works. But before that, you basically had the V-blank signal, and so you trigger the or like the vsync vblank whatever, you fill a buffer, and then at some point you tell the GPU, can you switch the current buffer that the display is scanning out from? And you had two options. One is you disable vsync, which means that you render a frame and then you change the current frame, and then if the display is in the middle of scanning out the display, right, then the portion that is not scanned out yet is gonna switch immediately sort of to the new buffer, and so you have tiering. Or you enable vsync, which means that the scan out, or like after you render the frame, you wait up until the scan out begins anew for the new cycle for the vblank signal. And then you have no tiering, but if your frame took 18 milliseconds to render, like if you miss the vblank by 2 milliseconds, you have to wait for 14 more if you have a 60 hertz refresh rate. And so the feature I implemented was pretty like a lot of titles I think used something like this. It goes like this. If you have just missed the vblank signal, so if the refresh, if the delta between like the last vblank and the and the current time, right, is within X%, let's say 20% of or like 10, let's say 10% of the of the target like frame rate. So if the display has started scanning out, but like the scan out position is within the 10%, then you do the flip, even if you are past the scan out. If it's further than that, or if it's been too short of an interval, like if the delta between the last vblank and the current time is like 8 milliseconds, then you also wait for the scan out. So you wait for a minimum of one scan out interval, but then if you are in the second scan out interval, and then if you are within the first 10%, you do the flip. And then if you are past this, for example, then you wait. Or there is a variation of this, which is if you are within the first scan out interval, you wait for this one. But if you're past this, you do the flip. I think the latter one is what we ended up shipping. Here's what this does. If your frame takes 15 milliseconds or 13 milliseconds or whatever, you do presentations lockstep with display, like rock solid 60 FPS. If you have a blip, like if you have a frame that takes 18 milliseconds or whatever, instead of delaying the next frame by a full like extra frame, you do the flip immediately, you see a tier line. And so for the frames that are longer than your refresh rate interval, you see the tearing, but you don't see tearing if you're making frame rate. So if you have a game that's optimized for 60 hertz, like you're generally running without vsync issues. The 10% variation of this that I mentioned, it would mean that if you ever see a tear line, it's only within the top 10% of the screen. This is just a dramatically better user experience for many reasons when you have uneven frame rate, which you always do. But to this day, so FIFO Relaxed does something like that, but FIFO Relaxed is supported by very few vendors. And so I think the reason is, you don't have the game context. But then if you do have the game context, let's say there's a game developer that wants this feature. How do you get this feature? You have to talk to multiple parties. You have to talk to your platform vendor, like Microsoft, who owns the presentation engine. If they need to make this happen, they have to ship a new version of Windows, which in the old days you would have to wait like years and years and years. So these days you have to wait at least 6 months, but actually probably a year to make any meaningful progress. But then also then Microsoft, I guess, has to talk to all of the different IGVs, convince them it's a good idea to implement in their graphics libraries, graphics drivers, stuff like that. So it's just a long pipeline with many different parties involved, and it's not heavily optimized it wasn't at all heavily optimized for the game applications, right? Similarly, I guess borderless full screen presenting without an extra composition copy is something that Microsoft did in Windows 10 creators update or something like this. So like a couple of years ago, 20 years into the development of Windows, you can finally have a full screen mode that is actually performant and simultaneously works well from the application, from the user's perspective of running multiple things on their machine. So it's just there's multiple different companies involved. They usually don't prioritize features that are important from the gaming perspective. And some of these features are difficult to ship, very difficult to ship in a cross-platform manner. For example, everything that Alan Ladovich, I don't know, from Crotech talks about in his really good presentation on GDC about micro-stuttering. All of this is stuff that is requires really intricate synchronization between various components that are involved in the system. These components are owned by different companies, and there's not it takes a dedicated effort to be able to ship a project like this, like end to end. And when there's not a single company that's driving this, it takes many years. And when the need isn't perceived to be really strong, it takes even more years, right? So I think this is sort of part of why all of this is difficult. But there's also other issues with this that are more intrinsic, around the fact that there needs to be a compositor these days, right? So you can't just take exclusive access for multiple reasons. Once there is a compositor, you need to find creative ways to bypass this. You need to ask questions: how does it work in windowed mode, etc., etc. So all of this stuff is also just intrinsically difficult to get through. But I think what you find is that when one company owns this end-to-end, then it takes a couple of years to figure this out. And when there's not a single company, it could take a couple of decades. All right. So with that, it's been a bit more than 3 hours. I have skipped the ARM question, but I am gonna just ignore that. And or I think I have 2 minutes to just finish this, which is to say, so as I was saying actually earlier in the stream, you should think about Apple and M1 separately from ARM for two reasons. One is the GPU stuff that they do is it has nothing to do with ARM. They have a completely custom architecture. My understanding, I won't say about the architecture, I don't know how much I can publicly say about this. So, but it's very, very different from ARM, both performance-wise and architecture-wise. If you look at ARM GPUs, they're just completely different. And then if you look at their CPUs, it's the same ISA, but it's a completely different CPU design. So again, ARM cannot replicate at all what Apple has done. And so what Apple M1 does is it demonstrates that you can build a really high performant ARM chip. And this is something that multiple companies, including ARM, have tried to tell the world for many years, but nobody has done this. Every ARM chip that you have today that you can look at is actually not great performance-wise. Like, it depends on what your comparison point is. Single-threaded performance tends to be from not interesting to abysmal, and then multi-threaded performance depends on the core count and such. But none of these are really great. Apple M1 is the first ARM CPU that's actually really great, right? It's crazy great. It beats the Intel and AMD competition. Even in many cases, if you exclude the terminal, if you ignore the fact that it runs at lower wattage, it still beats it in single core performance, which is just nuts, right? But this says nothing about the future of ARM. What would be interesting to see is the ARM GPUs, how the ARM GPUs evolve once NVIDIA acquires ARM, because ARM GPUs today are pretty, they're not fast. Like Qualcomm GPUs are faster. Qualcomm GPUs are faster. I'm not sure about PowerVR. But so ARM GPUs, I have really high hopes for, because I think NVIDIA really knows how to build GPUs, and so with NVIDIA ARM acquisition, maybe there's some cross-pollination of technology. CPUs, Apple proves it's possible to build a fast ARM chip, but Apple is the only company shipping a fast ARM chip today. So we will see how it goes. With that, thank you all very much for being on the stream, and I will end the stream. Hope everybody is safe out there. Take care of yourselves. Take care of people you love. And let's hope that the next year is going to be better than this year in many respects.